Hello, and welcome to Sleepy Science. Tonight we'll drift through time's quiet riddles. Seconds that stall while you keep moving. Minds that step outside the clock. Frozen instants that fake motion. Memories that edit the present. And phantom histories that still leave measurable fingerprints. Then test the causal lock, peek into a chrono-singularity where moments crowd together. Watch how simply looking can hold change in place. Open doors to nested realities and undying signals, and wander loops, leaks and silent beginnings with calm curiosity. Tell me where in the world you're listening from. Your city, your country, and what time it is. And if these slow explorations help you rest, please like, subscribe, and share so other sleepy minds can find their way here. Now take a deep breath. Let your shoulders drop and join me for an unhurried walk along the soft edge where time blurs, curiosity brightens, and wonder does the counting. When time stops existing and you keep going, you notice it first in the quiet, not in a laboratory, but in the ordinary space of your own life, when your eyes land on a wall clock and for a breath, the second hand seems to freeze as if the room had slipped out of gear, and yet you continue breathing, thinking, remembering, alive inside a moment that looks paused from the outside. What you're feeling isn't magic, it's your brain catching up, because every time your eyes jump from one point to another, they actually go blind for a slice of an instant, and your visual system backfills the missing time to make the world look smooth, stretching the first tick after you look so it feels longer than it was. A quirk called the stopped clock illusion that reveals a deeper truth. You never experience time raw. You experience a story assembled in your head, a fraction of a second late. And most days that delay is a gift because it holds your world together. Begin there, gently, with the idea that what you call now is already a reconstruction. Then walk into the next room where physics keeps stranger clocks. In school you learned that all motion takes place in time, like actors crossing a stage, painted with seconds, but step into relativity, and the stage itself bends, and how fast your clock runs depends on the path you take through space-time. If you race close to light speed or sit deep in a gravitational well, your seconds stretch compared with someone else's. And although your own heartbeat feels normal, you arrive to find more time has passed for those who stayed behind. This is not fantasy. It is how GPS satellites must correct their clocks to guide your phone. And it whispers something unsettling and comforting at once, that there is no single grand metronome ticking for everyone. Only many local times woven together. Press further, and you meet an extreme you can only point to with care, because particles of light trace paths for which the usual personal time, the kind carried by a wristwatch, adds up to zero, meaning that along a light-like path, there is no felt interval at all, and while a photon doesn't have a rest frame you can sensibly occupy, the mathematics is still telling you a story with a sharp edge. There are motions for which time, as we count it, effectively disappears. Yet, the world keeps unfolding around them. Now come back to your body, because your brain is not a clock with a single spring either. Instead, it's a network of timers, some tuned to split seconds so you can catch a ball, some tuned to minutes so you can keep a promise, and they live in many places. Circuits that coordinate movement, regions that predict the next beat of a song, areas that weigh reward and risk, and they can be pushed around by chemistry and context so that fear makes moments feel stretched, awe makes minutes feel wide, boredom makes them sag, and deep focus makes them evaporate. This is why a fall from a ladder can feel like slow motion without actually giving you time to think, because the brain lays down a denser memory track and, when you replay it, the recording feels longer than the event. And it is also why a sudden, unexpected sound can seem to last more than it should. The oddball effect that lengthens unfamiliar things in your mind to help you notice them, which is another way of saying your perception of time is biased towards survival rather than accuracy. All of that prepares you for a stranger turn. There are places in our best theories where time doesn't show up at the most fundamental level, where the master equation looks frozen and change seems to vanish until you choose part of the universe to serve as a clock for the rest. Some physicists argue that what you experience as time could be an emergent bookkeeping, a pattern that appears when systems correlate, like music rising from the discrete clicks of a metronome, only when notes are strung together, and whether or not that story is finally right. It teaches a practical lesson you can carry tonight, that what feels like an unstoppable river might also be a stitching, your mind binding separate frames into a narrative that can speed or slow or even, briefly, seem to stop without the world ending. You can test this safely by noticing how your now expands when you breathe slowly, how a minute stretches when you remove hurry, how a walk without your phone returns, edges to the world, and makes the day feel longer. Not because the earth spins differently, but because attention gives you more frames to weave. But you still want to know what it would mean for time to stop and for you to keep going, so gather what you have. A biology that edits the present, a physics that allows many local clocks, a technology that proves we already live in a patchwork of times, and a mind that can widen or narrow experience. Imagine a deep anesthesia where you wake and find no gap inside you, as if you teleported from before to after, or a dreamless sleep that erases hours so completely that your story runs smoothly across a canyon of unexperienced time. And notice how in each case your body continued, your heart played on, your cells repaired, the world turned. And what stopped wasn't reality, but your access to it. There are also forms of meditation and flow where your inner narrator grows quiet and the usual timestamping fades, not because the clock outside died, but because your attention ceased to measure in its ordinary units. And here again, the lesson is gentle. The feeling of time can drop out while life carries you. At the opposite extreme, stand near a massive object where gravity slows local processes and realize that while you feel normal, distant scenes will flicker faster by comparison. So in a sense, pieces of the universe have already learned to go on at different rates without tearing the whole apart. If this sounds abstract, bring it back to your next hour. The way you choose to look at moments changes how many you get to live inside. The way you organize attention alters the texture of the day. And even if we never freeze the cosmos with a switch, you can still experience honest pauses by noticing the seams your brain tries to hide, the jump of your eyes between words, the silence after a question before an answer arrives, the half second it takes sound to cross a room, because each seam is a place where the movie stutters and you carry on. And in that recognition, the fear softens, because you see that keeping going is what life does while your sense of time flexes around it, that your meaning is not in seconds, but in what you fill them with, and that the most practical power you own is not to outrun the clock, but to shape the richness of the moments it measures. So let the second hand stop for an instant, the next time you glance up, and take it as a quiet invitation, not to panic at the strange behavior of your perceptions, not to invent a story beyond what's true, but to remember that your present is a crafted window, and you can polish it by how you pay attention. Begin gently, grow curious in the middle, end softly tonight, with the simple reassurance that even when your sense of time falters, you don't vanish. You breathe, you notice, you learn, and that is you going on. The paradox of timeless consciousness. Your mind, outside the clock. You don't notice it at first because it hides inside what feels obvious. You live your life as if consciousness were a bead sliding along a wire of seconds, always arriving, never early, never late. And yet when you really pay attention, you find that awareness is less like a bead and more like a window that gathers light from a span of moments at once, a stitched now that floats above the clock rather than obeying it. Psychologists once called this the specious present, the small but elastic interval your mind treats as a single moment, and once you sense it, you start seeing the seams everywhere, not because anything mystical is happening, but because your brain is an editor that collects events, smooths their order, and only then lets you in to witness the final cut. Begin gently with something playful your senses do all the time. When a moving object and a brief flash appear at almost the same place, you often see the mover farther along than the flash, even though they were shown together. a sign that your visual system predicts motion and displays a slightly updated world rather than a raw feed. In other cases, a later cue can even reach back and change what you think you saw a heartbeat earlier, so that your conscious picture reflects not just what has happened, but what just happened after it. Postdiction, the mind's quiet habit of polishing the past before presenting it as the present. This isn't cheating. It's how a brain outpaces delay. Nerve signals take time, so your system forecasts, integrates, and corrects, making consciousness feel anchored while it actually floats over a brief window, gathering the near future and near past into a single now. Drift a little deeper, and you meet a second surprise. Your sense of when you act is also flexible, especially when you feel in control. In lab setups, where you press a button and a tone follows, the gap between action and consequence seems to shrink when the event is self-caused, a phenomenon called temporal binding that hints at a mind that bends its personal time to keep agency coherent. When you own an action, you pull its effects closer, knitting cause and result into a single experience, so the story of "you did this" holds together. Pair that with the attentional blink, the brief period after noticing one thing when a second thing slips by unseen, and you realize that conscious awareness is not a continuous spotlight, but a rhythm of openings and closures shaped by what matters to you. In fact, your brain runs on rhythms from the inside out, tides of activity that gate when sights, sounds, and touches get bound into one scene. And although scientists debate the exact timing, it's clear that a synchronized brain often binds a world that feels seamless while its clocks tick in layered, nested cycles. Now turn inward to the quiet metronome you carry in your chest, your heartbeat, and the nerve signals it sends to the brain with every pulse. Alter what you notice and when you notice it. Research shows that your sensitivity to faint flashes or fearful faces varies with the phase of the cardiac cycle, so the now you live in is partly written by a bodily drumbeat, a reminder that consciousness is not just in your head, but also in the timing of your flesh. Then widen to the senses working together. You feel a tap on your arm and hear a click. If their arrival times fall within a narrow window, the brain fuses them into one event, but if they drift apart, your mind pulls them back toward each other. Anyway, correcting their timing so the world stays plausible. This multisensory binding is why a dubbed movie can feel natural once your brain learns the offset, why the rubber hand illusion works best when touch and sight are nearly synchronous, and why your conscious now is always a negotiated truce between signals that travel at different speeds. Music turns this truce into a dance. Rhythms outside your skin entrain rhythms inside it, nudging neural cycles to align with tempo so strongly that you start predicting the next beat and feeling it slightly early. In that alignment, time can seem to breathe. Anticipation stretches, resolution collapses, and the present becomes a living groove that is as much expectation as perception, which is another way of saying your mind is not passively riding time, it is composing it. All of this sets the stage for the paradox in the title. If consciousness is built from predictions, backfills, bodily pulses, and binding windows, then the you that feels perfectly anchored to the second hand is standing on a balcony just above the clock, watching a woven tapestry that includes threads from moments that have already slipped by and threads from events not yet fully arrived. That's not a claim that time runs backward. It's the sober recognition that your awareness waits for enough evidence to assemble a scene and only then declares now, even if doing so means borrowing from a slice of the immediate future to clean up the recent past. Consider what this means for memory. Each time you recall an instant, you don't pull a fixed gem from a vault. You rebuild it using present goals and feelings, often smoothing gaps and sharpening outlines you never saw at the time, which means your inner timeline is constantly being edited by the present moment's needs. The past you know is a living document, and consciousness is both its reader and its editor-in-chief. Consider also what it means for selfhood. In split-brain studies, where the communication between hemispheres is disrupted, one side can act and the other side invents a reason after the fact, showing that a part of you is tasked with stitching actions into a coherent story, regardless of their true timing or origin. The interpreter inside you does not lie to harm you. It fills the silence so the narrative of a single self moving through time does not fall apart. And that story is precisely what lets you plan, learn, and remain accountable. There is a gentle, philosophical echo here. Some physicists describe space-time as a block in which all events coexist, and the sensation of a flowing present arises from how living systems model change. You don't have to pick a side in that debate to draw a practical insight. The flow you feel is, at least in part, your brain's real-time rendering of correlations, and the thing that moves is the window of awareness, not the universe itself. Add one last piece. Expectation is a time machine you use every day, in small ways that keep you alive. You step off a curb because you're already simulating where the car will be. You catch a cup because your hand arrives where it will land. And even your conversations depend on predicting the ends of sentences before they're spoken. When those predictions are strong, the world seems to arrive early. When they fail, it arrives late, and your subjective time dilates accordingly, which explains why novelty can slow the day and routine can make weeks vanish. Pull these threads together, and the paradox softens. Timeless consciousness is not a ghost escaping physics, but a mind that sits slightly outside the tick of any one clock by design, integrating across a window, aligning with the body's pulses, binding senses with forgiveness, compressing and stretching intervals to preserve meaning, and constantly revising the timeline so that your life is livable. Far from making experience less real, this flexibility is why reality holds, still long enough for you to act within it. So end softly here. If you sometimes feel you have stepped outside of time, in deep listening, in sudden danger, in awe so wide you lose the urge to measure, you are not breaking the universe. You are meeting yourself where your awareness actually lives, on the balcony just above the seconds, where you can choose what to attend to, and by attending, shape the size of your now. Carry that with you not as a trick, but as a practice. Because the better you understand how your mind makes time, the more gently and wisely you can spend it. Quantum resurrection. Could the universe reboot itself infinitely? You've seen a system crash and come back to life. A screen goes black, the world pauses, and then with a quiet breath, the logo returns and everything reloads as if nothing happened. So here's the question that keeps cosmologists awake on quiet nights. Could the universe do that? Not once, but over and over. A grand-scale reboot that wipes the slate, but keeps the laws that let new stories begin. To approach it honestly, you start with the arrow we all ride. The steady climb of disorder called entropy that makes ice melt, stars burn out, and memories accumulate, because any talk of resurrection has to explain how a cosmos racing toward heat death, a thin, cold future where energy is smeared and nothing interesting happens, could ever reset to a low entropy, dawn like the one we call the Big Bang. One family of ideas says the bang wasn't a true beginning but a bounce, a turnaround, when gravity, pushed to quantum extremes, stiffens space-time enough to stop a collapse and fling it outward again, replacing the singularity with a minimum size and a new expansion that carries fresh structure. And while the details differ, some models picture a slow, smoothing contraction before the rebound. Others imagine extra dimensions where brains collide. The shared promise is this: if bounces are real, the universe could be cyclic, not in perfect repeats, but in a sequence of eras, each with its own galaxies and histories, each born from the ashes of the last. Another vision comes from the far other end of time, where the universe has expanded so long that all massive particles have decayed and only radiation remains, leaving, as Roger Penrose argues, a world with no built-in notion of scale, no rulers, no clocks, so that the cold, empty future and the hot, dense beginning can be mathematically stretched into one another, linking the remote end of one aeon to the birth of the next in a conformal handshake, not a loop, but an endless chain. And while proposed imprints of prior aeons in the cosmic microwave background are hotly debated and far from settled, the philosophical bite is clear. Perhaps beginning and ending are only costumes that a scale-free universe can swap, when conditions are right. Push from a different angle and inflation enters, the idea that a tiny patch of space once ballooned incredibly fast, ironing wrinkles and seeding structure. In some versions, that inflating state never fully shuts off. It keeps expanding elsewhere even after our observable bubble forms. So, new bubble universes continue to nucleate like foam on an endless sea, each with its own Big Bang, and perhaps different settings for the knobs of physics. From the inside, every bubble feels like a unique creation event. Yet globally, nothing truly reboots because the inflating background goes on. And if that's right, what we call the universe is one bloom in an eternal garden. Not a phoenix rising from its own ashes, but a flower from a root system that never dies. Then there's a darker possibility with a similar architecture, vacuum decay, where our cosmos inhabits a metastable state, good enough for stars and life, but not the deepest valley in the landscape of possible energies. And quantum tunneling someday pops a bubble of a more stable vacuum that expands at near light speed, rewriting the laws within its wall. From the bubble's interior, that transition acts like a new Big Bang with new rules, a brutal reboot that doesn't resurrect our structures but does restart cosmic evolution. And while no one can predict if or when such a transition will occur, the logic is simple. If the current vacuum isn't the final one, the script can flip. Even black holes, those one-way doors for matter and light, have inspired baby universe conjectures. As extreme curvature forms a horizon from our view, the interior might pinch off into a separate expanding region with its own time, a new cosmos budding, from the death of a star, so that a universe rich in black holes becomes a nursery for offspring. And some have even speculated that the constants of nature might drift across generations in a kind of cosmic natural selection, favoring black hole-friendly physics. This is beautiful and audacious, but it remains speculative because the physics behind horizons is notoriously hard to verify, and the bridges predicted by classic equations aren't traversable in ways we can exploit. There's also the idea of recurrence, the thought that any finite system allowed to run long enough will, through sheer combinatorics, return arbitrarily close to a prior state. Apply that to a universe with a horizon and a finite entropy, and you get timescales so vast they make every star's lifetime look like a blink, raising chills like Boltzmann brains, random fluctuations that briefly assemble thinking observers out of thermal noise, and telling us that reboot might not mean a clean restart, but a rare, eerie echo. Yet here, caution is vital, because it's not clear our real universe meets the tidy conditions those recurrence arguments assume, and many physicists treat such outcomes as paradoxes that signal a misunderstanding of how to count states in cosmology, rather than predictions to embrace. Underneath all these scenarios sits the hard core of the puzzle. The second law doesn't blink. So any honest reboot must either transfer the old entropy elsewhere, redefine what counts as disorder, or engineer conditions in which the arrow of time can effectively reset. Bounces attempt this with contraction that smooths away complexity before the turn. Penrose leverages the disappearance of mass so that scale loses meaning and entropy can be reinterpreted. Eternal inflation hides the arrow inside endless creation, so young regions are always appearing. And vacuum decay simply starts a new chapter with a lower baseline. But in each case, there are open questions about testability and initial conditions, because a good cosmic story has to connect to evidence. Where does that leave you tonight? Lying in the dark, thinking about a universe that could die and rise again? Oddly grounded, if you let it, because the scientific content here is not a promise but a map of possibilities constrained by what we've measured. The sky's leftover glow tells us our universe began hot and dense. The distribution of galaxies hints at a period of rapid early expansion. Black holes truly exist and evaporate slowly in theory, and quantum fields can tunnel between states. We are not inventing from desire. We're extrapolating from real clues, then humbly noting where the trail vanishes into fog. The existential weight is gentler than it first appears. If reality reboots through bounces, aeons, bubbles, or buds in horizons, then endings aren't erasures, but transitions between regimes. If it does not, if our cosmos runs once from low entropy to thin silence, its unrepeatable arc doesn't cheapen anything. It sharpens it, because meaning doesn't wait for infinite lives to be real any more than a song needs endless verses to move you. The physics asks how patterns persist or restart. The philosophy asks what you do with a pattern you've been given. So as you listen, let the mind picture widen. Perhaps somewhere beyond what we can ever see, a contracting era has already poured itself through a quantum throat into someone else's dawn. Perhaps down in the heart of some black hole, a newborn space-time is unfolding, indifferent to ours. Perhaps the inflating sea keeps throwing sparks that take their own billion-year breaths. Or perhaps this one universe will drift into quiet, and that will be enough. None of these options require myth. All of them require patience, and each one returns you to the same practical truth. Between beginnings and endings, you have a window where complexity blooms against the odds, and your awareness is part of that bloom. So you hold the thought lightly, you stay honest about what's known and what's guessed, and you let the possibility of cosmic resurrection make you a little more careful with this particular run. This one awake stretch between a past you can't reach and a future you can only imagine. The silent collapse, how time could secretly end without you noticing. Imagine waking up one morning and nothing is wrong with the coffee, the sky, or the sound of your own breath. No sirens, no cracks in the air. Yet in a quiet, literal sense, the future has stopped expanding toward you, as if the corridor you've always walked down simply narrowed to a final doorway you can't see. That is the unsettling idea behind a silent collapse of time, not an explosion or a rewind, but an end of newness that could arrive without a bang, because time, for creatures like us, isn't just a number on a page, but the steady arrival of differences you can notice and record. And if the universe starves those differences, your clock can keep ticking even while time, in the meaningful sense, runs out. Begin with a simple rule. A clock is anything that changes reliably, and the arrow of time is bound up with change that leaves records. Warm coffee cooling, stars burning fuel, signals crossing space. So if you imagine a universe that drains, its gradients using up the easy energy that drives contrast, you also imagine the slow drowning of the very processes that make time feel like motion. This isn't superstition, but physics. In a cosmos pushed by dark energy, expansion accelerates and faraway galaxies slip beyond a horizon from which light will never reach us. The background glow from the Big Bang gets stretched into wavelengths, too long to detect, and the sky simplifies until only our gravitationally bound island remains, dimming with each dead star. No cosmic announcement, just an information diet so strict that tomorrow contains fewer new facts than today, and an arrow of time that hasn't reversed or shattered so much as faded into near uniformity. Take that horizon seriously, and you meet the first way time can end quietly, causally, not globally. An event horizon doesn't ring a bell when you cross it. Whether it is the cosmic horizon that seals off distant regions in an accelerating universe, or the boundary around a black hole, and in both cases there is no local shock at the line. Nothing to feel with your feet, because horizons are about what signals can reach you, not about a wall in space. Fall toward a supermassive black hole and the crossing itself is uneventful. Yet from the outside you seem to freeze and fade, and from the inside your own future ends in a finite stretch of personal time, at a place no message can escape. A brutally honest demonstration that the end of time is not a universal curtain drop, but the quiet failure of further moments to be connected to you. Now turn from horizons to the calendar we draw on the sky. Cosmologists use different time parameters to make sense of the whole, and one of them, a map-friendly coordinate that rescales expansion, can actually run out in a universe dominated by dark energy. By that measure, the infinite future gets compressed into a finite coordinate length. So on that map, time really does stop at a definite value, even though your wristwatch would continue. An example of how an end of time can be a change of geometry rather than a loud physical event, the way a river on a flat atlas reaches the edge while the real water keeps flowing on a sphere. There is a second quiet ending, more operational than cartographic. If time is defined by the production of durable records, bits written, memories stored, then any world that slides toward equilibrium also slides toward an end of usable time, because turning change into memory costs free energy. As the temperature differences that power life and culture disappear, so does the ability to keep writing the future into matter. And long before the last star fades, the constraints of thermodynamics begin to pinch, narrowing what any mind can do per unit of heat, until now becomes a maintenance loop that rarely adds new structure to the archive. You don't hear this ending, you discover it in the growing sameness of things to measure. There is a third path, rarer and controversial, but still honest to discuss. If the energy driving cosmic acceleration is not perfectly steady, but slightly phantom, the expansion could outrun every bond in the universe in a finite time, galaxies unbound, solar systems undone, even atoms pulled apart in the final instance. Yet the creepy part is how long it would feel normal, because locally, measured seconds can seem ordinary right up until the forces you trust lose their grip. A catastrophic finish without a trumpet in the distance. Current observations do not require this scenario, but they don't forbid it strongly enough to erase it from the menu. And its lesson, like that of the horizon, is that the end need not come with a warning label you can sense in advance. Step back and connect the threads. None of these endings ask the universe to break its own rules. They all flow from ordinary principles. Signals have limits. Maps can be finite, even when roads are long, and records cost energy. So, the silent collapse is less a plot twist than a limit case of the rules we already use. You've seen hints in small things. A conversation that trails off because neither person has more to add, but no one announces goodbye. A city street after a storm where nothing moves yet, the clock on the bank still blinks. A streaming video that continues to count minutes while the image freezes. Functionally, time has ended for the task at hand because there is no more difference to register, even though the device measuring duration keeps working. Scale that intuition to the cosmos and you see how your personal second hand can go on while the supply of meaningful nexts dries up. This is not meant to be bleak. It is clarifying. It tells you what to watch if you want to know how much time you really have. The flow of information, the reach of signals, the gradients you can still use. Because those are the ingredients that turn duration into lived history. It also explains why you wouldn't notice until the notices stop. Why a universe that ends causally or operationally doesn't flip a switch in your body first. And why the first unmistakable sign might be the absence of signs. And it leaves you with one practical, almost tender conclusion. The opposite of a silent collapse is a noisy present, rich in contrast, where you deliberately cultivate differences worth recording. Learning one new fact, meeting one new mind, looking up before another galaxy slides below the horizon of what your life can touch. Because whether the far future is a tranquil de sitter hush, a cartographer's endpoint, or something stranger, your experience of time is built from notice and novelty, and the most honest way to resist an unnoticed ending is to keep enlarging the part of the universe that can reach you and be changed by you. One attentive breath, one small signal, one bright record at a time. Reality without duration, a universe made of frozen instants. Press pause on the whole universe, not just your screen, not just your breath, but everything, and picture a single, perfectly still frame that contains you mid-blink, a tree mid-sway, a photon mid-flight. Now imagine that this frozen slice is all that truly exists, complete and self-consistent, and that what you call motion and time are what your mind reads when many such slices are arranged by hidden rules, the way a flipbook becomes a running horse when your thumb slides fast enough. This is the intuition behind a universe made of instants without duration, and it's stranger, more scientific, and more honest than it first sounds. Because physics allows, and in some approaches even prefers, descriptions where the fundamental object is not stuff evolving in time, but a landscape of possible configurations, linked by constraints, so that change is the pattern that makes some frames neighbors and others nonsense. And your experience is the story told by climbing that pattern, one admissible step at a time. Start with something your own eyes already know. The brain can conjure motion from still images. The phi phenomenon is why a theater can flash 24 pictures per second, and your mind reports fluid movement. Similarly, a single frame can carry convincing traces of a past it does not literally contain. Footprints in snow, growth rings in wood, the layered salt of an ancient sea. And from these static marks, you infer a narrative that stretches before the picture. This is not a cheat, it's how inference works, and it hints at a deeper possibility some physicists and philosophers take seriously, that each now could be a complete, timeless configuration containing durable records. And what we call the arrow of time is the regularity with which those records within admissible frames point in one direction when you order the frames by their physical consistency. To see how this can be more than poetry, shift from the everyday to the blueprint. In classical mechanics, you can specify the state of the world with positions and momenta at an instant and then derive a unique future and past. But that same mathematics can be rephrased as a giant web of relationships among allowed states. The conservation laws are edges in the web, forbidding jumps that break energy, momentum, or charge. In quantum theory, the state of a system sits as a point in an abstract space, and the dynamics is a rule that assigns which other points fit, and in some attempts to weld quantum theory to gravity, a master equation appears with no explicit time variable at all, pushing you to treat becoming as being with correlations, not because someone wants to be mystical, but because the variable we used to call time may not survive at the smallest scales as a fundamental ingredient. None of this commits you to a universe with literal frame rate. The tempting number called the Planck time is often introduced as a smallest tick, but the data we have, gamma-ray bursts that arrive without energy-dependent delays up to astonishing precision, gravitational waves that match predictions for a smooth spacetime, atomic clocks that agree to more decimals than you will ever need. Do not demand that time be pixelated. Instead, frozen instants is a claim about description, not granularity. The world can be captured as a set of complete snapshots plus rules that tell you which snapshots stand side by side in a lawful sequence. What would make one frame neighbor another? In a mechanical system, tiny changes that preserve constraints, like slightly different positions that still satisfy a spring's length, form a path through configuration space. In a cosmic system, neighboring might mean frames whose matter distribution differs by a small lawful deformation, with light and gravity arranged, so that records in the later frame credit their origin to structures in the earlier frame. You do not need to compute this. Your life is built on it, because your memories are stable patterns etched in neural tissue, your photographs are pigment arrays that survive, and each now you inhabit includes reliable encodings of events that your current frame labels before. Even if, in the deepest bookkeeping, there is only this configuration has within it patterns that match other configurations placed in a particular order. You might ask, if only instants exist, why does motion look continuous rather than jumpy? Part of the answer is biological. The nervous system integrates over small windows and predicts ahead, but part is structural. The laws that connect admissible frames reward smoothness, because continuous symmetries and the conserved quantities they imply severely constrain which sequences are physically possible. The horse in the flipbook is a lie because its frames are not tied together by conservation of momentum or by the propagation of signals at finite speed. But the universe's flipbook, if that metaphor fits at all, is locked by deep regularities that make jagged, discontinuous stories vanishingly rare. What about a truly discrete world? Atoms of space-time, causal grains that accrete into larger patterns. Some research programs explore exactly that. Causal set ideas treat reality as a partially ordered collection of elementary events, while other approaches quantize geometric properties such as area and volume. These aren't proven, and they disagree on details, but they hint that continuity might be an emergent habit, not a requirement. Crucially, none of them gift you with an obvious global time flowing through the set. Instead, they give you orders and adjacency, and you reconstruct a sense of before and after from the network structure, just as you reconstruct a river's course from a map of its tributaries. If this leaves you feeling like a still life with a pulse, notice what a single still can contain. The microwave background pattern written across the sky is a fossil of a hot, young universe. A zircon crystal holds isotopic ratios that, in that one mineral now, encode radioactive chains that ticked for billions of years. Dorsal hippocampal neurons in your head, as they fire right now, carry a compressed elsewhere, elsewhen, that lets you navigate a city you are not currently in. Within one instant, the world stores its own archaeology. And if you believe that lawful frames tend to be those that maximize the consistency of such records, you can see how a run of frames in which records stay reliable will feel like a life, lived in forward gear, even if the book of reality is, at root, a catalogue of self-consistent pictures. The test of an idea is not whether it flatters our intuitions, but whether it connects to evidence and suggests searches. A universe of frozen instants makes crisp predictions only when married to a detailed scheme for neighbor relations, and that is where the frontier lies. We look for minute violations of the symmetries that keep sequences smooth. We watch for dispersion of high-energy light that would betray a granular background. We hammer on time translation invariance with ever better clocks to see whether identical processes truly take identical durations today and tomorrow. So far, the world answers with remarkable steadiness, which supports the conservative view that time works astonishingly well as a smooth parameter, but leaves open the possibility that smoothness is a large-scale mirage cast by deeper, timeless rules. What does all this teach you, practically, beyond the intellectual thrill? It says that continuity in experience depends on the reliability of records, so meaning lies in what gets written into the frame you actually occupy. The care you take with your memories, the signals you send, the knowledge you preserve. It says that if change is the pattern connecting complete pictures, then your choices are the micro-edits that help decide which lawful sequence you inhabit, not by willfully violating physics, but by selecting among the many neighbor frames compatible with the one you're in. And it says that awe, the sense that you are briefly seeing the world outside the clock, may simply be your awareness leaning back far enough to glimpse the stillness in which all motion is composed. End there, gently but firmly. Whether the universe is fundamentally a river or an atlas of lakes, your life is the crossing of a landscape full of traces, and every truthful frame you help make, every clear thought, every careful measurement, every small act of preservation improves the story that can be read from a single instant, which is to say, it gives the next lawful picture more to inherit. And if reality truly has no duration beneath the seams, that inheritance is exactly how you move. Reverse time echoes. What if you're hearing the future right now? Close your eyes and listen to the room you're in. The faint hum, a distant car, your own breath. And consider a possibility that feels like a magic trick hidden in plain sound. What you hear as the present may already contain traces of what hasn't quite happened yet. Not because physics lets messages travel backward through decades, but because your auditory system quietly waits a sliver of a second, samples the next few moments, and then edits the timeline it gives to your awareness so that the world sounds stable. Begin there with the simple fact that sound takes time to reach you. Nerves take time to fire, and the brain takes time to decide. So if it delivered raw input the instant it arrived, your experience would stutter, drift, and often be wrong. And instead, it uses a short integration window on the order of tens to a couple of hundred milliseconds to combine what just came with what is arriving, which means your conscious now in hearing is a carefully produced blend that can include very near future cues. Push on that idea and it gets delightfully concrete. In speech, the identity of a consonant is often disambiguated by what follows, the next vowel, the hiss of the next fricative. So your brain doesn't fully lock in the earlier sound until it has peaked at the acoustic future. In music, the system that tracks rhythm locks onto patterns of timing and timbre so strongly that it predicts the next note and, when the prediction is confirmed, tightens your sense of when the last one occurred, giving you the feeling that the beat was always there all along. In the lab, there's backward masking, where a quick, loud sound that comes after a soft one can make you fail to hear the soft one at all, essentially letting the future overwrite the immediate past inside that integration window. And there's phonemic restoration, where noise hides a missing syllable and your language circuits fill it in so convincingly, guided by words that come later, that you remember hearing a sound that never reached your ears. None of this requires superstition. It's a survival strategy. Because the world is noisy and echoes scramble timing, your brain is a prediction and correction machine that takes out temporal insurance by briefly waiting to see what happens next, then backdating the best story of what just happened so your actions line up with reality. Even outside speech and music, hearing keeps a running bet on the future. Neurons in auditory cortex shift their firing depending on expected patterns. Midbrain circuits adjust sensitivity to anticipated onsets, so you detect the important click against a sea of noise. And the networks that localize sound fuse the arrival times at your two ears over a short span so that reflections don't yank the perceived source around the room. Again, the future few tens of milliseconds stabilize the present. If you worry that this is cheating, notice that it's honest about limits. The brain's look ahead is tiny, measured in fractions of a second. You can't learn tomorrow's lottery numbers by listening harder, but you can navigate a busy street because your auditory system is quietly forecasting the next thrum of a motor and using it to refine where the last one belonged. Now zoom out to physics, and you'll find that time itself is less bossy in the equations than it is in your intuitions. Many of our fundamental laws work just as well if you run them backward, and engineers exploit that symmetry in time reversal, acoustics, recording a messy burst of ultrasound in a reverberant medium and then playing the recording backwards through an array so the waves unscramble and refocus on the original source as if they knew where to go. Nothing supernatural is happening, no message from the future, just a clever use of reversible wave math to make echoes behave like homing pigeons. A reminder that the line between past and future in sound is thinner than it feels and can be manipulated without violating causality. There's a deeper point here about information and arrows. The universe enforces a one-way direction for large-scale processes because entropy tends to increase. But at the scale of milliseconds and wavefronts, time symmetry gives you wiggle, room to do retro tricks locally, undo a smear, refocus a pulse, let later samples sharpen earlier ones, so long as you never create a paradox. Your brain has been doing a version of that all along, using a tiny buffer and clever inference to make a coherent present from messy arrivals. That brings us to the provocative question in the title. Are you hearing the future right now? And the careful answer is yes and no. You are not receiving facts from next week, but your auditory experience of this moment is allowed to include information that technically came later than the sound it clarifies. And that post-dated correction is baked so deeply into perception that you rarely notice it until an illusion reveals the edit. It's why a sudden clap after a soft tone can erase the tone in memory. Why a word can become another word after you've heard more of the sentence, and why a rhythm can feel perfectly steady, even if the first few beats were slightly crooked. This matters beyond curiosity because it reframes how you trust your senses and how you design the world around them. Public address systems that account for reverberation feel clearer because they work with your brain's integration window, instead of against it. Hearing aids and cochlear implants perform better when their processing respects those predictive windows. Audio for virtual and augmented reality becomes more convincing when it feeds your expectant circuits, the tiny anticipations they crave. And your own listening becomes kinder when you remember that comprehension blooms a fraction late. So pausing before you reply isn't slow, it's neurologically honest. End softly on the human note. The idea that your present contains a breath of the future isn't a threat to truth. It's a testament to how much care your nervous system invests to keep you synced with a slippery world. Hearing is not a camera taking snapshots. It's a composer assembling a bar of music while the last notes are still ringing. And once you know that, you can listen differently, more patiently, more precisely, and maybe with a little wonder at the quiet editor inside you who is always gently keeping time. Phantom timelines. When the universe creates histories that never happened. Picture a crime scene with no culprit. Footprints cross fresh snow, the door is ajar, a cup is warm. And yet, the cameras show nobody entered. Your mind stitches a plausible backstory because the clues demand one. But what if the universe itself sometimes does this? Building outcomes from patterns that imply histories that never actually occurred, phantom timelines that are consistent, measurable, even, essential to the calculations, yet do not exist as lived sequences. Begin gently with a fact at the heart of modern physics. When we predict what a particle will do, we don't just trace one neat route from start to finish. We add up contributions from every route it could have taken. Short, long, looping, absurd. And the real outcome is sculpted by the way these imagined paths reinforce or cancel one another. Nothing mystical there, just the sum over histories method that explains why interference patterns appear on a screen, even when you send particles one by one. The bright and dark bands record how ghost routes you never observed shaped the probability of what you do see. And in that sense, the experiment carries the fingerprints of many alternative journeys that never unfolded as facts. Push deeper, and the story gets stranger but more precise. In the consistent histories approach, you don't ask the world to commit to a single classical storyline. You let it offer many coarse-grained narratives, sets of events that hang together without interfering, and you accept that different, incompatible narratives can each be valid on their own terms, but cannot be merged. In one such narrative, the particle went through the left slit, in another the right, and in a third, neither path is assigned because interference was preserved. And the rule is simple and mercifully honest. You must not combine these accounts into a single, overloaded past, because quantum mechanics forbids a universal, all-at-once timeline that answers every past tense question at once. Pick a framework, and a past becomes real within it. But resist the urge to mix frameworks, or you will create contradictions no experiment can support. Now add a twist that sounds like science fiction, but is laboratory work. In a quantum eraser, you give a particle a tag that would reveal which path it took and thereby destroy interference. Then later, you erase the tag's information before you finally look at the pattern. When you keep the which path data, the record you collect supports a history of definite paths. When you erase it, the record supports a history in which the particle kept both possibilities alive long enough to interfere. Nothing traveled backward. In time, no fate was rewritten. But your late choice of what information to keep determines which consistent past you are allowed to reconstruct. One timeline becomes phantom because you refuse to keep the clues that would have made it coherent. There is an even subtler way the universe lets you learn from what did not happen. The interaction-free measurement. You can design a setup where a perfectly sensitive bomb would explode if and only if a particle took a certain path, and, yet by arranging interference cleverly, you can sometimes infer the bomb's presence without triggering it, meaning your detector lights up precisely because a path was available but went unused. The avoided detonation leaves a real mark in your data, a trace of a route that had to be possible in order not to be taken, and that counterfactual shadow is as solid a fact as any bang. In the same spirit, counterfactual computation lets you extract an answer from a quantum device in a way that, with high probability, implies the computer would have produced that answer had it run, even though in that branch it didn't. Run. Your final output carries the weight of a computation that, in your actual timeline, remained a phantom. If you think that's as far as the rabbit hole goes, consider the method of conditioning on both what you prepare and what you later find, pre- and post-selection, and asking what weak, non-invasive probes in between tend to report. Sometimes, the intermediate weak values you read out look impossible from any single classical path, as if the particle left faint traces along mutually exclusive routes. You're not catching the world in a lie. You're discovering that when you filter reality by both its beginning and its end, the best-fitting story can assign influence to segments of history that no single sharp measurement would ever confirm. As the path, a reminder that retrodiction in quantum land can be a mosaic assembled from shards that never align into one classical film. Zoom out to the largest scales, and a different kind of phantom timeline haunts our inferences. Thermodynamics tells us countless microhistories can lead to the same tidy macroscopic present. This mixed air, that lukewarm coffee, the sky's calm glow. So when you reason backward from the state of your room, you are choosing among vast numbers of plausible pasts. Most are nonsense, but even among lawful microstories, there are unimaginably many. And without an assumption that the universe started in an extraordinarily special, low-entropy condition, the past hypothesis, you would be forced to accept grotesque phantom explanations like your present, with its memories randomly fluctuated out of equilibrium, a possibility the equations allow, but that good reasoning rejects because, given the data, a long, orderly past is far more probable than a freak fluctuation that forged a fake history in one go. That's the critical insight. Some phantom timelines are permitted by the math, but we keep them out of our worldview by weighting them fairly against the evidence we actually have. Even relativity offers a gentle hint that history is not one absolute film, but a family of cuts through space-time. Two observers moving differently can disagree on the order of distant events that cannot influence each other, so there is no single global before and after to impose on those scenes. Pick a motion, pick a slicing, and you get a different narrative that all observers agree leads to the same measurable outcomes in the end, while other orderings become merely descriptive phantoms relative to your chosen frame. Astronomy turns this into a visual lesson. Strong gravitational lensing can give you several images of the same background quasar, arriving along paths of different length and delay. Watch blindly, and it looks like 3 separate outbursts in 3 different timelines. But model the lens, and you learn to collapse those conflicting stories into one real event, plus a set of path-dependent echoes, phantom histories that make sense only if you forget the warping glass between you and the source. Pull these threads together, and you get a posture toward truth that is both humbling and empowering. The universe often builds the present by letting many would-be histories participate mathematically and then eliminating all but one when records are written. Some of those eliminated stories are not mistakes. They are the scaffolding that shaped what survived. In the lab, we can revive their influence with erasers and weak probes. In logic, we can quarantine them with consistent history rules. In cosmology, we can avoid them with fair priors on the past. And in daily life, we can remember that our neat explanations often overreach by mixing clues gathered under incompatible conditions. End softly here. Phantom timelines are not a license to believe anything. They are an invitation to read reality with care, to ask which records exist, which questions can be coherently combined, and which beautiful backstories our brains have invented because footprints begged for a walker. The universe is kinder and stranger than a single film strip. It lets alternative plots audition. It casts only one for the final cut. And it leaves, if you know how to look, the faintest signatures of the scenes that never made it to the screen. The causal lock, a reality where you can't escape the next second. You feel it most on nights when the city goes quiet and the hum of your own body becomes the loudest sound in the room, a steady current of life carrying you forward whether you agree or not. And somewhere between one breath and the next, a thought appears that is both obvious and unsettling. No matter what you decide, the next second is coming and you cannot step outside it. Begin gently with the plainest reason this is true, which is that the world is stitched by continuity. Things that exist have to become the things that follow from them without tearing. And continuity is not a gentle suggestion, but the first. Lock on reality. The rule that a cup cannot be on the table and in your hand in the same instant without passing through the brief, lawful states in between. That a storm does not teleport, but grows from pressure and heat that were already there. That your heart beats, because electrical waves travel through tissue along paths that existed a moment earlier. And beneath all this is the insistence of nature that causes sit next to effects in space and time. That influence radiates outward, no faster than signals can travel, building a boundary around what can possibly change in the next heartbeat. Physicists draw that boundary and call it your future light cone, but you do not need the diagram to feel the rule. You cannot snap your fingers and move the moon. You cannot learn a message from a star that has not had time to reach you. And, even inside your own skin, the state you are in limits which states you can reach one instant later. Muscles that are contracted cannot be simultaneously rested. Memories you've not laid down cannot already guide your hand, and a word not yet chosen cannot have been spoken, so the corridor into the next second is narrow, not because the universe is cruel, but because it is coherent. Push deeper, and you meet the second lock, an informational one. The present is thick with records, arrangements of matter that encode what has already happened. And those records are not decorations, they are constraints. The dents in a car, door, the pattern of soot on a chimney, the protein configurations in your neurons that hold a phone number are all commitments the world has made, and any future that contradicts them is simply not an allowed future. This is why reality does not branch into outcomes where the cup refills itself, or the broken plate is suddenly whole without a trace, because the records would have to be rewritten in a way that leaves no mark of the rewrite, and ordinary processes cannot do that without paying a price. When engineers erase a bit in a computer, they must dump heat somewhere, and the same is true of every attempted undoing. The accounting of information insists that an honest universe carries its history forward as inertia you cannot shed for free. So even if the laws at the bottom are flexible about running forward or backward, the way information is stored in the world locks the direction. The next second must be a continuation that respects what is already written. Add the third lock, an energetic one, and the corridor narrows again. You get a future to the extent you have gradients to drive it, differences in temperature and potential that let work be done. Your brain is a hungry heat engine that burns sugar and oxygen to maintain structure against decay, and your sense of agency is built on the reliable availability of that energy flow. In a room with no food, no oxygen, and no sunlight, choices vanish. Not because your will collapses, but because the physical currency of change is missing, and at the grand scale, the same truth is written across galaxies. Stars shine, and planets cool because there is still free energy to spend. And when that allowance thins, the space of possible next seconds shrinks with it. You do not need to tell a gloomy story about the end of the universe to see the local point right now. Every action, from a sentence you write to a jump you attempt, must be paid for in energy and will therefore be one of the futures that budget allows. Put these locks together: continuity, records, energy, and the phrase causal lock stops sounding like a prison and starts reading like the reason you can count on anything at all. And yet, you might object, what about indeterminism? The idea that at small scales outcomes are not fully fixed in advance. The fair answer is that uncertainty does not break the lock, it changes its character. If the dice of nature are a little noisy, the next second may come with several allowed microversions, but you still cannot escape having one of them, and you cannot have one that violates the neighborhood rules of continuity, the honesty of records, or the budget of energy. A raindrop may wander left or right on a window pane, but it will not jump into steam without heat or climb the glass against gravity without a source of push. And a neuron may or may not fire on a threshold, but it will not communicate faster than its channels allow or encode a memory that conflicting inputs forbid. Chance preserves the lock by making the next second a set of lawful possibilities instead of a single path. and your life unfolds by selecting among them, not by cancelling. The second itself. Relativity tightens the picture with a geometry lesson that matters more than it sounds. Your motion through the world changes which events are even eligible to affect you next, because the speed limit on signals doesn't only slow radio messages and rockets. It orders reality into can reach you soon and can never reach you in time. And this order is not a moral rule, but a structure in the fabric. You can only dance with the partners who are in the same ballroom, and the ballroom keeps shrinking as you move faster. Not because the universe has a grudge, but because that is how influences fit together without contradiction. The block universe picture, where all events exist in a timeless whole, is one way to think about this structure. And whether or not you adopt that view, it delivers a practical truth. No observer, no matter how clever, has access to a universal reset button that skips the queue of causes. And any future you actually live must be connected by lawful paths to the present you occupy. Psychology adds a quieter, kinder version of the lock you feel every day. Your brain runs on predictive control, constantly forecasting what the next fraction of a second will bring, so it can place your eyes, your hands, and your thoughts where they need to be. In that sense, you are always slightly ahead of yourself, and that is still part of the lock, not an exception to it, because the predictions you rely on are trained by the world's regularities. When you walk downstairs, you do not choose whether gravity will apply on the next step. You choose how to work with it. When you speak, you do not choose whether air will vibrate. You choose which vibrations carry meaning. Freedom shows up not as the power to escape the next second, but as the skill to shape it from inside the corridor the locks provide. If this feels confining, notice the flip side you might have missed. A world without the causal lock would be unbearable because plans would not cash out, promises would not hold, and care would not matter. The only reason effort works is that reality insists the next second be welded to this one. Practice improves outcomes because small changes propagate. Reliably, knowledge helps because records constrain futures. Technology functions because energy budgets are predictable. The lock is why a seed becomes a tree and not a cloud. Why a vaccine reaches a target and not a random organ. Why a letter sent today arrives tomorrow rather than last year. The same structure that forbids you from slipping outside time is the one that protects you from a chaos in which nothing follows from anything. So end softly with a reframing that is both honest and useful. You cannot escape the next second, but you are not its prisoner. You are its author within limits, a participant who can tilt probabilities, arrange conditions, and build records that will constrain tomorrow in your favor. Continuity means small acts accumulate. Records mean truth can be kept. Energy means resources can be stewarded. And together, they give you a kind of freedom far more interesting than fantasy. The freedom to do work that lasts. Take one slow breath. Feel the corridor open just enough to step into it with intention, and let the certainty that the next second is coming be the most practical kind of hope. The precondition for every change you still want to make. Chrono-Singularity, where all of time collapses into a single point. Imagine a map that shrinks forever into a dot and still tells the truth about how roads connect. A cartographer's trick called conformal compactification that physicists use for spacetime, where an entire infinite future can be drawn as a single tidy point without lying about which events can influence which. Begin there, because chrono-singularity sounds mystical. But the first lesson is practical. Sometimes all of time collapses only on the map, not in the territory. The way a globe's pole is a point that stands in for unending lines of longitude. In a Penrose diagram of our expanding cosmos, the distant future of a patient observer can be shown as a single point labeled time-like infinity, and nothing breaks. Light cones still tilt properly, causal paths still thread the page. So the collapse is a compression for clarity, a reminder that the words we use about time often mix pictures with physics. Now turn from maps to events where the collapse is not just ink deep, but dynamical. because general relativity contains places where every admissible future for a traveler really does end at a single boundary in finite personal time. Fall into a sufficiently massive black hole, and, after crossing a horizon that feels locally ordinary, you will meet a space-like singularity in a calculable number of heartbeats. Not a place in space, but a limit in time where your world line cannot be extended any further. That is what singularity means in sober terms. Geodesic incompleteness. And it's the second kind of collapse. All the tomorrows available to you are gathered into a short proper interval that terminates as surely as a river meeting rock, because the geometry inside forces every path toward the same temporal cliff. Importantly, this endpoint is not a dot you could visit and return from, nor a magical bead where events are stored. It is the failure of the equations to provide more moments to live, and it is as physical as tidal forces that grow without bound. A similar but time-reversed compression frames the beginning of our observable universe. If you ride backward along the smooth cosmic time that works so well after the first fractions of a second, you reach a past boundary where densities soar and the usual description breaks. In the simplest Big Bang models, that boundary is a singular surface. Again, not a speck in space, but a moment no earlier slices can cross. So the entire prior of every comoving observer is collapsed in that coordinate to the same temporal edge. Modern cosmology is careful here, because quantum gravity may soften that edge into something like a bounce or a smear. But the classical lesson holds. In our best tested equations, there are places where before and after cease to be extendable ideas, and in that sense time truly does narrow to a point. Before you conclude that collapse is only for extreme gravity, meet a quieter, observer-made version. Accelerate hard enough for long enough. Think of a rocket that never stops firing, and a horizon forms behind you, a boundary beyond which events can no longer send signals that catch up. For you, the accessible slice of the universe is a finite causal diamond, and the far past and far future of regions outside it compressed to your horizon in the same diagrammatic way as eternity, compressed to a dot on the earlier map. Add the Unruh effect, the prediction that a constantly accelerated observer would detect a warm bath of particles where an inertial observer sees vacuum, and you get a vivid moral. Time's content depends on how you move, and the edge of what you can ever experience behaves like a surface on which vast stretches of elsewhere and elsewhere are encoded, that leads naturally to holography. The idea made precise in black hole thermodynamics that a horizon's area measures how many independent ways the region can be configured, and in the more speculative CFT correspondence that a lower dimensional boundary theory can capture the entire bulk's physics. In that holographic sense, a lifetime of falling matter can be represented by a change in a surface's degrees of freedom, a kind of bookkeeping collapse of many minutes and meters into bits on an edge, different from smashing time itself, but strikingly like it in spirit. Complex histories compressed into compact summaries that still predict the right outcomes. A third, laboratory tame route to all of time in a point, hides in the behavior of systems at criticality. As a material approaches a continuous phase transition, its correlation length grows, and the time it takes for disturbances to relax grows with it, critical slowing down. So from the viewpoint of the order parameter, the system's internal clock stretches toward infinity, and a wide span of microdynamics gets crushed effectively into an unchanging state. If you sketch the evolution with the right rescaled variables, whole hours of microscopic jostling collapse to a fixed point of the renormalization group, a mathematical object that summarizes how patterns look when you repeatedly zoom out. You can watch this in fluids that turn milky at their boiling point, in magnets near their Curie temperature, in neural avalanches that flirt with scale-free bursts, long movies recoded as still portraits that retain the logic of what matters. Again, the theme repeats. No fairy tricks, just lawful compressions where many steps of time are faithfully represented by a compact descriptor. There is yet another angle from the foundations. Some approaches to quantum gravity and to the foundations of statistical mechanics suggest that what we call time flow may emerge from the state of a system rather than being laid atop it, like grid lines, so that at true equilibrium, the generator of change becomes trivial. There is nothing left to count, no gradient to follow, and the natural parameter that moves states along their modular flow goes flat. In that thermal time picture, a chrono-singularity is not a tear but a loss of contrast. The moment a description's internal clock has nothing left to tick about, and it connects with a practical truth you can feel. A page full of repeated symbols carries less of a story than one with differences to track, and the first page of a novel encodes an hour's worth of attention only because it resists being summarized. Where compressibility is perfect, duration is cheap. Pull these strands together and you see why the phrase, where all of time collapses into a single point, can be both a mapmaker's convenience and a physical fate, both a horizon's accounting trick and a phase transition's fixed point, both a black hole's terminal wall of moments and a cosmologist's boundary for the beginning. You also see why responsible awe requires distinctions. A Penrose dot is a picture of an infinite tale, not a cosmic guillotine. A singularity is a limit to further moments, not a dot in space where a traveler could wait. A horizon is an observer-dependent edge that gathers far histories into a surface description, not a curtain with a sign that says the end. And a fixed point in condensed matter theory is a compression of time's details, not their denial, ends softly but firmly with the human consequence. The universe seems to have honest ways to summarize, bound, or even terminate stretches of time. But those ways never cheat the causal structure. They respect what can touch what and how effort accumulates, and that is exactly why your finite days can add up to lasting structure. You cannot keep eternity from being drawn as a point on someone's diagram, and you cannot rescue an infaller from a singular future, but you can choose descriptions that reveal, rather than obscure, how histories get compressed into boundaries and summaries. And in doing so, you learn to read reality's maps without mistaking them for the territory, a skill that, in a world so often tempted by shortcuts through time, is its own kind of freedom. Borrowed time. What if every second you live is an illusion? Start with a confession that feels like a magic trick you were never told. Every second you live is partly made up, stitched from agreements and guesses. So when you glance at a clock and trust the neat march of digits, you're leaning on a story that machines and minds work hard to keep straight. Begin gently with the machines, because even there a second isn't a gift from nature, but a definition. We decided to anchor it to the steady beat of a particular atomic transition so our clocks wouldn't drift with the wobble of Earth's rotation. And ever since then, civil time has been a negotiation between two tempos, the clean swing of atoms and the messy day-night rhythm of a planet slowed by tides and winds. So we literally borrow and repay seconds to keep them aligned, sometimes inserting a leap second, so midnight contains 60, sometimes smearing that extra second across a minute so computers don't hiccup, sometimes shifting whole hours in and out for daylight saving, moving the wall clock by decree. Stand at an airport crossing the international date line, and you can gain or lose a day without your body changing at all. Proof that your calendar is a social technology, not a law of physics. And even the most perfect atomic clocks announce a strange truth. Put one on a high shelf and one near the floor, and the higher one will tick imperceptibly faster because gravity warps time, which means two people in the same room do not age at exactly the same rate. None of that breaks your life, but it should nudge you toward the deeper part of the title. If the machine second is a carefully maintained convention, your felt second is even more of a construction. Inside your head, there is no single metronome, but a thicket of timing systems tuned for different jobs. Circuits in the basal ganglia and cerebellum help you tap a beat. Prefrontal areas estimate intervals for planning, and neuromodulators act like gain knobs on the flow of moments. Change dopamine, and you change time's pace. Stimulants and excitement can make intervals feel longer while they're happening, because the internal pacemaker runs hot. Whereas low dopamine states, fatigue or depression can make minutes feel thin and fast, as if the world were slipping past with fewer snapshots. This isn't superstition, but laboratory fact. People with Parkinson's disease often underestimate durations. ADHD shifts timing precision, and your own experience of a frightening near miss or a thrilling performance stretches because arousal sharpens temporal resolution, letting you pack more events into the same wall clock span. That split between objective and subjective shows up in two daily illusions you can test without a lab. Prospective time, the time you feel while you are waiting, lengthens when attention sits on the clock, but retrospective time, the time you judge after an hour has passed, lengthens when memory is dense. That's why a boring afternoon crawls in the moment, but looks short in hindsight, while a travel day flies by as you live it, but looks long later because your brain stored many scene changes, and researchers call this the filled duration effect. Populate an interval with events, it seems longer afterward. Leave it empty, it shrinks. Space itself biases your timing, and timing biases your space. In the Kappa effect, we judge intervals between flashes that are spread farther apart as lasting longer, even if the real durations match. And in the Tau effect, flashes that are timed farther apart feel farther apart in space. A reminder that your brain assumes motion is smooth and borrows from where to help decide when. Your estimates follow a simple law across tasks. Errors scale with the size of the interval, so the fuzz in your seconds grows with the seconds themselves. And when you must guess without strong anchors, you drift toward the middle, which is why advice like "speak for a minute" is reliably misjudged unless you practice with feedback. Now add memory's quiet edits, because what you call a moment is partly a reconstruction driven by goals. When you concentrate hard, fewer episodic markers are stored and the day compresses in hindsight. When you seek novelty, new streets, new songs, new recipes, your brain lays down more boundaries and the week expands when you remember it, which is why years feel faster as you age if routine deepens, and why deliberate novelty is a practical way to slow the felt passage of life without changing the clock. Aging also brings a proportion effect. The 10th summer of a child is a giant slice of lived experience. The 40th summer of an adult is thinner by comparison. So the same calendar month is worth a smaller fraction of your story and, therefore, feels shorter unless you counterweight it with variety and attention. Technology edits your seconds too. Audio and video players hide small network delays by buffering then releasing a smooth stream. Navigation apps predict your car's next position and correct the path on the fly. Stock exchanges care so much about ordering trades that they build time servers in guarded rooms and argue about nanoseconds. All of that infrastructure exists because raw time is messy at the edges, and our systems routinely borrow a few milliseconds from the future to clean up the jaggedness of the present, just as your senses do. Even culture decides what counts. As now, prayer times tied to the sun, work shifts tied to factory whistles, school bells corralling childhood into 40-minute blocks. Each a human frame laid over a biological clock that still keeps circadian time in the suprachiasmatic nucleus tugged by morning light and midnight screens. If you're worried that calling seconds illusions makes the world untrustworthy, consider the more generous reading. An illusion here isn't a lie, it's a useful rendering. The way a map simplifies reality so you can navigate. Atomic seconds let a planet's irregular spin talk to our schedules, and subjective seconds let a limited brain act in a noisy world by focusing on what matters. The cost of those renderings is bias, but biases can be known, and once you know them, you can steer around them. Practical translations fall out quickly. If you want time to slow down as you live it, attend closely to the moment. Meditation and deep play increase the number of frames your mind registers. If you want time to feel full when you look back, seed your calendar with firsts, new places, skills, people, so memory has texture to encode. If deadlines devour your sense of control, clock your work in ultra-short sprints and brief rests to give your internal timers honest feedback. If waiting tortures you, move your attention off the clock and onto a task with measurable progress, because prospective time dilates under watch. If evenings evaporate into screens, set cues that break the stream into chapters. Walk, write, call. So the night earns more beads on the string of memory. End softly on the phrase that brought you here. Borrowed time is not a curse, but a reminder that every second you feel and schedule is a loan you co-author with physics, culture, and brain. You will never hold a pure, godlike instant in your hand, but you have something better, the ability to choose the rendering you live by, to invest attention where it stretches your life, and to forgive your perception when it bends, because that bending is what lets a finite human keep pace with an infinite world. The memory trap. Is time just your brain, playing old recordings? You think you're moving through time like a traveler on a road, but most days the road you feel under your feet is paved by memory, layered, edited, and replayed. So ask it a gently unnerving question. How much of your now is the brain sampling the present, and how much is it stitching in loops of stored experience to make the moment make sense? Begin where the machinery is clearest, in the hippocampus, a seahorse-shaped structure that doesn't keep your past like a library, keeps books, but like an index points to where the story can be rebuilt, binding together sights, sounds, places, and feelings into episodes you can revisit. Inside that index, scientists have found place cells that fire in specific locations, and time cells that fire in reliable sequences across a few seconds. A living metronome that steps through a scene so your brain can tell before, from after, and when you rest or drift towards sleep. Those same patterns replay in fast forward during tiny electrical bursts called ripples, compressing minutes of life into split-second rehearsals that help stabilize what you learned. Sometimes the brain even pre-plays, running a likely future route before you walk it, showing that memory is not a vault, but a simulator that projects possibilities using fragments of the past. This is why a smell can pull you across years. In an instant, retrieval isn't opening a file, it's reinstating the pattern of activity that once defined a moment, reactivating a network across cortex so vividly that you feel transported. And yet that transport is never perfect, because remembering is reconstructing, not rewinding. Each recall passes the memory through today's goals and emotions. And when the memory is set back down, it can be altered in small ways. A process called reconsolidation that makes the past a living document. It's why flashbulb memories of public shocks feel photographic and still drift measurably over time. Why witness accounts, sincerely told, can diverge after discussion, and why a small suggestion after an event can smuggle in a detail. That becomes part of what you remember. The experience is real, but its content is negotiable. Your brain helps itself along with schemas, templates about how restaurants work, how streets unfold, how conversations go, and those schemas fill gaps so that the world doesn't stall every time a scene is incomplete. When you walk into a familiar kitchen, you don't relearn where cups live. You let the template pre-fill the room and then update it with any surprises. That same habit operates in time. You expect that after a click comes a whir, that after a question comes an answer, and you feel a smooth present, partly because memory supplies the expected next frames. Break those expectations sharply by changing context, crossing a doorway, switching tasks, and the hippocampus marks a boundary, cutting one event from the next and resetting those internal time cells, which is why the minute after a transition can feel wider and why days rich in clear boundaries are easier to remember as long. Under the hood, there is also a context signal that drifts slowly as you live, a kind of internal background that co-changes with whatever you're doing. The brain binds experiences to that drifting context, so when a cue brings the context back, the associated episode is more likely to pop into awareness. This reinstatement is what mental time travel is made of. You don't slide down a tube to yesterday, you rebuild enough of yesterday's neural state that it feels like standing in its light again. And if the rebuilt context is slightly off, you can get déjà vu, a tension between familiarity and recall, where the system flags, "I've been here," without retrieving the specifics to prove it. None of this means the present is fake. It means the present is a negotiated space where incoming data and remembered patterns meet, and the trap is mistaking a successful negotiation for raw reality. Your sense of duration bends under memory's hand too. When an interval is packed with landmarks, new streets on a walk, distinct scenes in a movie, it seems longer in hindsight because memory saved more flags, while a smooth, repetitive interval shrinks after the fact. This is not a trick but a strategy. Your brain expands what is useful to revisit and compresses what would only clutter the archive. Sleep turns the strategy into policy. In deep sleep, those hippocampal ripples help train the cortex to hold the essentials so the index can eventually let go. And in REM, the brain recombines fragments into strange narratives that may look chaotic but serve a purpose. Testing which patterns belong together, exploring variations, stress testing predictions, so that tomorrow's now runs on a better model. In waking life, brief rests can trigger micro-replays that refine a motor skill or a map of a city, quietly improving the next attempt while you tie your shoe. Because memory is used to predict, it can also dominate when input is poor. In a foggy room, you are more likely to hear the word your brain expects. In a dim hallway, you are more likely to see the shape that fits the scene. And on a bad day, you may interpret a neutral glance as a threat because a similar past is gripping the present. This is the cost of a powerful simulator. The more it has helped you before, the more tempting it is to let it drive. And noticing that pull is the first step out of the trap. There are also lifespan patterns worth knowing so you can steer them. Most adults remember little before age 3 or 4 because the brain systems for stable episodic memory and narrative self are still wiring then. Later, memories cluster around late adolescence and early adulthood. The reminiscence bump, because those years are dense with firsts and identity-making events. And as routine grows, memories thin unless you deliberately seed novelty, which is one reason time can feel faster with age. None of this is fate. Variety, attention, and reflection are tools you can use to enrich the record your future self will play. So, is time just your brain playing old recordings? No. And yes, in the way that matters. Physical time is out there whether you notice it or not. But psychological time, the one you live by, is a film constantly edited from archived scenes to keep you oriented and safe. The honest posture is not to scold your brain for filling gaps, but to partner with it, giving it better material to work with and checking its edits when stakes are high. Practical moves follow immediately. Create clear event boundaries if you want days to feel longer in memory. Walk a new route. Mark the end of work with a small ritual. Write briefly about meaningful moments within 24 hours to stabilize details before reconsolidation drifts them. When two people disagree about what happened, ask what each of you had reason to expect. Often the schema, not the senses, is to blame. And when fear or shame loops a memory too tightly, bring it back gently in safe conditions so the brain can rewrite the emotional tagging without erasing the truth, turning a trigger into a lesson. End softly here. Your life is not a tape that wears thinner each time it's played. It's a living score that can be recomposed, a museum that adds wings and updates labels, a map that sharpens with each careful survey. The present you feel is richer because memory is working in the background, and the wisdom is not to resent that help, but to guide it, curate what you store, notice how you rebuild, and choose the stories that keep your now honest, curious, and kind. Quantum ghosts, events that exist before they're born. Imagine an image appearing on a camera that never saw the object. No lens pointed at it. No light bounced from it into that sensor. Yet when you later compare the camera's clicks with a second detector that did touch the object, a clear picture emerges, as if a ghost had carried the scene across space. Begin here because it sounds like a parlor trick and is instead a sober experiment called ghost imaging, where a crystal creates pairs of linked photons and you send one partner to interact with the object and fall into a simple yes-no bucket, while the other partner flies to a high-resolution camera that looks at nothing at all. And only when you correlate the two streams after the fact does the hidden image bloom from the statistics. Nothing supernatural happens. No message outruns light. No secret tunnel connects the paths. Yet the result forces a new sentence into your vocabulary. There are patterns in the world that exist only in relationships, so that an event you care about becomes visible only when a later record is used to sort earlier clicks into meaning. And it is in this careful sense that quantum ghosts feel like events that exist before they're born. Push deeper, and the theme sharpens in another laboratory story that feels like a riddle answered with electronics. You make two independent pairs of entangled particles, label them AB and CD, and send A and D to distant detectors to be measured in ordinary ways, while B and C linger near a device that can, if you choose, measure them jointly in a way that projects them onto a shared pattern. When you select that joint measurement and then go back and look at the records, you find that A and D, particles that never met, display the telltale connectedness of an entangled pair, as if a bond had been written between them after they were gone. Call this entanglement swapping, and be precise about what it does and does not mean. It does not let choices in the present rewrite outcomes in the past or send a message to yesterday, but it does reveal that correlations in your data can be defined by a decision made later, and that the event you are tempted to imagine, a pair coming into existence as a single system, has no standalone reality without the full pattern of measurements that cradle it on both sides of time. If that sounds like wordplay, try a different kind of ghost, one that flips your everyday intuition about motion. You prepare a wave packet of a quantum particle so that every momentum component points forward. Yet for a brief span, the probability of finding the particle in a region can flow backward against the sign of its momentum. This quantum backflow doesn't shove a lump of matter upstream, and it never violates the speed limit on signals, but it shows that the bookkeeping of chance itself can slosh in directions classical reasoning forbids, a pre-echo of absence where presence should be growing. It is a reminder that even without any talk of observers and choices, quantum states can carry interference that toys with where the future's weight appears, leaving a measurable dent in where we expect the next detection to be. A quieter class of ghosts haunt the vacuum itself. When you compute how an electron interacts with light, you cannot ignore the fleeting contributions of fields that are never directly observed, fluctuations that crackle in and out of the math. And although these offstage actors are not particles marching through time like marbles in a tube, their influence leaves crisp fingerprints in the real world, shifting the energy levels of atoms, nudging the magnetic moment of the electron away from a simple value and producing a tiny force between metal plates placed a hair's breadth apart. Here again, the event that matters to you, a spectral line in hydrogen, a measurement in a magnet, carries the imprint of processes that you cannot point to as standalone happenings, more like shadows in a ledger than characters on the stage, and yet indispensable to the plot. Return to imaging for a moment and notice a practical kin of these ideas. In heralded experiments, a click in one detector announces that its partner must be present in another arm of the apparatus, so you can open a gate or start a timer with confidence before the partner is ever directly registered. Your later decision to keep only the trials with a heralding click doesn't send any influence backward, but it does let you treat earlier intervals as if a signal were already there, because the physics of the source guarantees the pair's joint birth, turning conditional knowledge into a kind of retroactive existence in your data. This is how you do delicate measurements with single photons, and how you build quantum networks that depend on trusting correlations rather than on bright beams. The same relational logic shows up when two quanta that never meet still agree about an outcome through a device that mixes their possibilities. Send one photon into each input of a beam splitter, and, if they are truly indistinguishable, they will exit together in lockstep rather than separating, a phenomenon that draws a dip in the coincidence counts when you slide their arrival times into perfect overlap. Look closely, and you see why it belongs in this chapter. No single track carries the explanation. Only the joint amplitude of both ways at once does. And the pattern that matters is written across two histories that you cannot peel apart into what happened first. If you are tempted to leap from these experiments to time travel, pause and reread the rules they demonstrate. The future does not transmit usable information into the past, but later records can sort earlier noise into legible events, and in that sense, many of the things you care about in quantum physics, images, bonds, even absences, are born in correlations rather than in isolated moments. The ghosts are not lies. They are structures that never live in a single place or time, and they vanish if you insist on looking at only one stream at a time. What does this buy you beyond a satisfying strangeness? It buys tools. Ghost imaging lets you form pictures in harsh conditions because the camera that reconstructs the scene can sit far from the fragile beam that touches the sample. Entanglement swapping is the backbone of repeaters that will one day link quantum computers across continents, extending fragile connections by stitching together local pieces after the fact. Sensitivity to vacuum ghosts gives you metrology so precise it checks the consistency of modern physics at many decimals. And even backflow, once a theoretical curiosity, inspires ways of thinking about wave control and probability transport that could influence how we design sensors. End softly with the human lesson hiding under the lab equipment. In the quantum world, what counts as an event is often less like a brick falling and more like a chord struck across instruments in different rooms. You hear it only when you listen for harmony. The past is not rewritten by the future, but the story you can justly tell about what occurred is sometimes decided by how you read the full score, and learning to be honest about that. Celebrating the ghosts that live in lawful relationships, while refusing myths of messages from tomorrow, is part of what it means to understand time at the smallest scales without fooling yourself. The loop. You can't escape. Could you already be reliving this moment? You know the feeling because it sneaks up between blinks. A crisp, eerie certainty that you have stood in this exact breath before, as if the world were on a treadmill and your life had been set to repeat. So ask the unsettling question honestly, could you already be reliving this moment? And then answer it with care by separating three very different kinds of loops the universe offers. The ones on paper, the ones in matter, and the ones in minds. Begin gently with the paper loops, where mathematics allows tidy returns that reality rarely grants, because there is a famous theorem that says a perfectly isolated, finite system will, given long enough, come arbitrarily close to a previous state again, a Poincaré recurrence. And it's the sort of line that tempts headlines about cosmic déjà vu, but the fine print is the lesson. Arbitrarily close is not identical. The system must be sealed against leaks it never truly avoids, and the waiting time is so immense that a star would go cold a quintillion times over before your coffee cup had a chance to nearly revisit its starting arrangement. So the math says, loops are not forbidden, but the universe you live in is too open, too noisy, and far too large to hand you a literal rerun of your Tuesday. Shift to loops in matter and you meet a humbler, more practical kind that engineers and physicists use every day, where systems are coaxed to unwind some of their own scrambling to produce an echo of an earlier signal. In nuclear magnetic resonance, an MRI for example, the tiny magnets inside your tissues fall out of step because of local differences, and a clever sequence of radio nudges flips the crowd so that the same differences now pull them back into alignment, producing a bright spin echo. A revival that briefly recreates a past coherence without pretending the world ran backward. In delicate quantum devices, researchers do a cousin of this: perturb a system, let it evolve, then reverse the sign of the disturbance and watch how well the original pattern reappears. An echo whose sharpness tells you how quickly microscopic chaos and environmental noise shred reversibility. In cold atoms and trapped ions, you can even see revivals, where a wave packet that had smeared out regathers rhythmically, not because time loops, but because many frequencies beat against one another and briefly resynchronize like a choir, finding the same chord again. These are honest, laboratory-proved ways a system can revisit a recognizable state, and their limits are the point. The more complex and open the world, the less perfect the echo, which is precisely why life flows and does not stall. You might ask whether space-time itself could make a tighter loop, and general relativity does offer strange solutions in which a path through the universe bends back to its own past, a closed, time-like curve. But the price tags are steep. Rotating universe, models that fail basic cosmology, hypothetical cylinders or cosmic strings that demand impossible densities, regions near spinning black holes where the mathematics goes suspiciously flexible. Add to that a consistency rule many physicists take seriously, that if such loops ever exist, only self-consistent histories can occur, no grandfather paradox allowed, and a widely held suspicion called chronology protection. The idea that quantum effects would explode any would-be time machine before it formed. Taken together, the sober reading is that nature is extraordinarily hostile to literal time loops big enough for people, and we have exactly zero evidence that macroscopic closed curves through time are part of our world. Which brings you to the loops in minds, the ones that can make the present feel like a rerun, even when physics refuses. Your brain is a prediction engine running in cycles, sampling the world several times a second and comparing what arrives with what it expected. When sampling and motion line up just wrong, you can experience the wagon wheel illusion. Under steady light, a spoked wheel can appear to freeze or drift backward because your perceptual snapshots alias the rotation. An honest reminder that experience is built in loops and can mislabel change. Deeper in the machinery, corticobasal ganglia circuits learn habit loops by chaining cue, routine, and reward. Great for tying shoes and terrible when rigid routines make days collapse into sameness, and hippocampal networks can replay and pre-play brief sequences to consolidate learning and plan paths, which sometimes leaks into awareness as a false familiarity that people call déjà vu. None of that is trickery for its own sake. Cyclic sampling and rehearsal are how a slow, noisy brain stays in sync with a fast, cluttered world. But it means the sensation of repetition can be a side effect of a system doing exactly what keeps you safe. Put the pieces together, and the answer to the title becomes clearer and kinder. In a strict, physical sense, you are almost certainly not trapped in a literal loop of time. No hidden conveyor is dragging you through an identical copy of this second, but you are surrounded by lawful echoes and cycles that can make a moment feel reborn. Spins in your body, refocusing into an echo that lets doctors image your heart. Atoms in a trap, singing back a pattern they seem to lose. Instruments in your head sampling the room and sometimes mishearing motion as repetition. Learned behaviors that close on themselves until you intervene. And because the loops that matter most are the cognitive ones, you have leverage. Inject novelty to thicken memory so days don't flatten. Mark clear chapter breaks to prevent routines from blurring. Vary prediction by seeking new inputs, so the mind stops autoplaying yesterday onto today, and when a bad loop persists, change the cue or the reward and the routine will follow. End softly with the paradox that should comfort you. The very structures that can make life feel circular, feedback, resonance, rehearsal, are the ones that let you improve, because echoes carry information you can use. You do not need a time machine to escape a loop. You need a new signal to lock onto, and the evidence from physics and from your own nervous system agrees. Time is not a prison that forces you to relive the same instant. It is a medium in which patterns can be revived, revised, and, with a little skill, rewritten. When the universe runs out of next, the end of causality. Picture a massive library where every page is stamped with a tiny arrow, showing which pages it can legitimately lead to next. And imagine that living in a universe is like reading such a book. Causality is the rule that says you may only turn to pages the arrows allow, never skipping to endings that aren't connected. Begin gently with the modern, practical meaning of that rule. Cause and effect are not moral categories, but a geometry of influence that tells you which events can reach which others by signals that never outrun light, and the shape of those can-reach relations is what physicists really mean by the structure of time. When that structure is well behaved, you can take a single snapshot of the world, positions, fields, the state of matter on a slice, and the laws will let you compute a lawful tomorrow for every point you can touch. a property called good predictability that underlies everything from weather models to why your coffee cools and not the other way around. The title question asks what it would mean for the universe to run out of next, and the first honest answer is simple and startling. Next ends wherever the arrows end, and there are several ways nature can erase arrows without making a sound. One way is dynamical. General relativity, our best-tested theory of gravity, allows regions where the book of space-time literally has no next page for a traveler. If you cross certain boundaries inside a spinning or charged black hole, you encounter a limit beyond which your path cannot be extended. Not because a wall blocks you, but because time itself runs out of extendable moments. That boundary is a singular end in the sober sense that every possible tomorrow for you is compressed into a finite personal interval. And while faraway observers see nothing dramatic at the instant you cross, your own line through reality terminates. At a genuine no more, a true end of causal possibility. Nearby to this lies a different, subtler failure of next. In some solutions, the equations predict internal Cauchy horizons, where the laws no longer deliver a unique future, even if you knew the present perfectly. Too many pages would be allowed, predictability shatters, and causality as a clear ordering of events dissolves into ambiguity. Most researchers suspect nature protects us from that chaos. Tiny disturbances inside black holes are believed to amplify so ferociously that those horizons become destructive, restoring the harsh finality of an end rather than the confusion of too many futures. But either outcome is an end of next in a precise sense. The arrows either stop or multiply into noise. A second way is global and patient. In a universe dominated by a repulsive energy that drives accelerated expansion, distant regions slip permanently out of touch, and the set of pages your part of the cosmos can ever reach shrinks to a bounded collection. Inside that causal island, free energy is slowly spent. Records become harder to write, and the number of distinct, stable arrangements you can realize with the matter and energy left to you declines. You don't need catastrophe to run out of next. You can run out of difference. The arrows degenerate, not because they point nowhere, but because they all point to states so similar that no new information gets written. It's like reading a book that keeps offering the same two endings with different punctuation marks. Legally, there are still pages to turn, but operationally, there is nothing left to change. That's an end of causality measured not in bang and crash, but in the exhaustion of gradients that make causes bite. A third way is microscopic and strange. At very small scales, the universe can play looser with order than your intuition expects, and researchers have built devices where two operations occur in an indefinite order. The outcome is not A then B or B then A, but a controlled superposition of both. No paradox is created, no message arrives before it is sent. But the clean single-file queue of causes is replaced by a softer rule in which correlations are real, while their order is not. And if such indefinite causal structure turns out to be more than a laboratory curiosity, then next is not so much gone as dissolved, replaced by linked without a definite sequence. You still can't violate the iron rule that usable influence never outruns light, but the bookkeeping of first and second can blur, and with it a piece of what you casually mean by cause. There is also an austere statistical sense in which next depends on counting. Whenever you bound a region by an energy budget and a boundary size, physics places a limit on how many bits of distinct state it can carry. Spend all those bits on storing what has happened and on maintaining equilibrium, and you limit how many distinct futures can still be encoded without overwriting the past. Much as a full hard drive can only accept a new file by deleting or compressing an old one. Causality continues to hold in principle. The arrows are still there. But the space of distinguishable necks collapses because representation itself is at capacity, and in that informational sense, a patch of universe can arrive at the end of its causal creativity long before it arrives at any literal boundary. If these endings sound abstract, test them against your real tools. Hospitals run MRI machines by exploiting echoes that temporarily reverse small patches of microscopic disorder, and the sharpness of those echoes is a measure of how quickly True causality, irreversible, arrowed, reasserts itself. Astronomers watch black holes shred stars and see no hint of negotiable rules at the edge. Satellite clocks, correcting for gravity's effect on their rate, show daily that who can influence whom is a geometric fact, not a cultural preference. And quantum experiments that toy with order never hand you a time machine, they hand you a resource for computing in new ways, without untying the deep knots that keep cause and effect from collapsing into nonsense. Pulling the strands together, you can now give a careful answer that respects both science and the human hunger for meaning. The universe runs out of next, wherever either geometry forbids new links. Predictability fails to deliver unique continuations. Resources drain until differences cannot be made, or order melts into indefiniteness that no longer supports a single-file story. None of this requires myth, and none of it trivializes action. In fact, it elevates it. Because as long as your local arrows still point forward and gradients still exist, you get to decide which lawful branch you follow, which records you write, which of the remaining pages you make real. End softly here, with the thought that causality is not a prison but a promise. It tells you that effort can matter because tomorrow is welded to today, and understanding where next can fail is not a reason to despair, but a map of where attention counts most. While there are still arrows to choose among, your choices are how the book continues. Hidden symmetries, physics that works perfectly without time. Take away every clock on Earth, every ticking hand, every digital colon, and ask a bolder question than it first appears. If you stripped time out of the description of nature, would physics still work? Would the world still make testable predictions? Begin gently with a picture you can feel in your hands, a planet's path drawn as a single closed curve on paper. Once you know the mass, the pull, and the angular momentum, the whole orbit is fixed as an ellipse, with no stopwatch required, because conservation laws born from symmetry tell you the shape outright. Time, in that drawing, is only a label that says where on the ellipse the planet happens to be when you look. But the ellipse itself, the hard content of the law, was determined without marching forward second by second, and that is your first glimpse of physics without time. Rules that specify the set of allowed configurations and the relations among them, leaving when as a choice of coordinates rather than the engine of truth. Push that idea deeper, and you meet a principle that quietly powers huge swaths of science. Nature often chooses paths not by stepping through time, but by satisfying a condition on the whole path at once. In the least action view, you give a system two boundary posts, start and finish, and the actual trajectory is the one that makes a certain global scorecard stationary. No timer appears in the scoring itself, just the geometry of possibilities, and the requirement that small deformations of the path don't improve the score. From this single timeless rule you can rederive Newton's laws, light's path through glass, and much of modern field theory. It is a stunning economy. Instead of telling the universe how to move every instant, you tell it what counts as a legitimate history, and the movie emerges as any convenient way of parameterizing that history after the fact. Symmetry is the quiet hero here because whenever a law is unchanged by a transformation, shift the whole lab in space, rotate the apparatus, slide the description forward in time, something measurable is locked in place. This is the content of a theorem every physicist leans on even when they don't name it. Invariance under shifts in time corresponds to a conserved quantity we call energy. Invariance under shifts in space corresponds to momentum. Invariance under rotation corresponds to angular momentum. The moral is simple. The more symmetry you have, the more you can say about what will be true without tracking the story frame by frame. It's why you could predict the existence of planetary orbits from symmetry and gravity long before you could time a single full revolution, and why a gyroscope stays upright. Not because you constantly calculate its future, but because rotation symmetry forbids certain changes unless torque pays the price. If this sounds like a trick for simple systems, step inside your living room. The patterns of a guitar string or the resonances of a room are found by dropping time entirely from the equations and asking for spatial shapes that fit the boundaries. Standing, waves whose form is fixed by length, tension, and geometry. Once you have the shapes, you can always hang oscillations on them later. But the what can exist part is timeless. The same move powers quantum mechanics in practice. Before you ever compute how a state evolves, you often solve the time-independent problem to find the allowed patterns of probability in an atom, and those patterns, energy levels and orbital shapes, explain spectral lines, chemical bonds, and much of the periodic table without narrating any second-by-second evolution. Engineers lean on this every day: bridges, rooms, antennas. Even MRI scanners are designed by finding modes and constraints, timeless skeletons of behavior from which time-domain responses are then stitched as needed. Now turn to gravity, where the point becomes philosophical as well as practical. The equations that describe space-time don't come with a universal clock tucked inside. They're written to be indifferent to how you slice the four-dimensional fabric into space now plus a next one. And that indifference reads like a rule. Only relations that don't care about your bookkeeping deserve to be called physical. Pick one slicing and you get one time. Pick another and you get a different one. Yet both are just different ways of walking across the same set of invariant relations. Many researchers say it this way: time in such a theory is a parameter. We choose to describe change, not a substance the world runs on. If you want predictions, you anchor one physical process as a clock, an atomic transition, a pulsar's beacon, the slowdown of a cooling lump, and you state other processes relative to it. That relational recipe is not hand-waving. It is how real measurements work. Your phone's navigation depends on tiny differences between clocks at different altitudes and speeds, and the theory doesn't ask which time is true. It asks which comparison is invariant, then tells you what you will read when you compare. There's a more startling version of this no built-in time even in the foundations of quantum theory married to gravity. Some of the flagship equations that try to describe the universe as a whole don't feature a time variable at all. They demand that the allowed states satisfy a constraint that reads in plain words: the generator of time flow vanishes, which sounds like a paradox until you learn to ask more humble questions. Not, how does the universe evolve, but what correlates with what? In that view, a prediction is a conditional statement. If a certain atom has ticked n times, what is the distance between these galaxies? If a detector finds energy E, what is the probability that another device registers a partner click? Truths about linked readings, with no narration about an external clock. Far from being esoteric, this conditional attitude matches how experiments are reported. You publish joint distributions, not metaphysical declarations of now. Notice how this unlocks surprising power. By focusing on invariants and constraints, you can solve problems that look impossible in the time domain. Celestial mechanics reduces to geometry when you trade time for angles and areas and exploit conserved quantities. Complicated networks of springs, beams, or electrical elements yield to symmetry methods that classify modes by how they transform under rotations and reflections. Even in statistical physics, some of the most successful predictions, how gas pressure relates to temperature and volume, how magnetization disappears at a critical point, arise from counting possibilities consistent with symmetries and constraints, not from watching every particle collide in sequence. The world turns out to be deeply overdetermined by its hidden order. And when you find that order, you need very little when to say a lot of what. If you worry this demotes time to a mere human fiction, step back and draw the boundary. Clearly, none of this denies that processes unfold or that clocks tick differently in different conditions. Instead, it relocates time from the throne to the tool bench. You can always introduce a parameter that increases along lawful histories and call it time. Choose proper time along a path. Choose the reading of a cesium atom. Choose the phase of a wave. And then rewrite the equations to track change with respect to that parameter. But the content that survives changes of viewpoint. The part we all agree on, no matter what clock we bring, is encoded in the symmetries and constraints. That is why two teams on opposite sides of the planet, using different apparatus and different schedules, can still agree on the mass of the Higgs boson or the frequency of a spectral line. They are measuring invariance, not the theatre schedule of reality. The human consequence of this is both practical and oddly calming. When you design, model, or simply try to understand a system, look first for its hidden symmetries, the features that remain unchanged when you shift, rotate, rescale, or relabel, and for the constraints that carve the possible from the impossible. Those give you handles you can trust even when the clock is noisy or the data comes late. In a lab, it means solving the static problem before you chase dynamics. In daily life, it translates into something humbler. Many problems get easier when you stop asking, "How long will this take?" and start asking, "What must be true at the beginning and at the end, and what is conserved in between?" Constraints, budget, energy, attention are your invariants, and plans built around them are more robust than those that worship a deadline. End softly with the thought that physical law is kinder and deeper than a stopwatch. Beneath the rush of seconds is a scaffolding of relations that doesn't age, and the more fluently you read that scaffolding, the less you need time to make sense of change. Physics works perfectly without time, not because time is unreal, but because the universe's most honest statements are about what stays the same when everything else moves. And once you learn to hear those statements, you carry a quieter kind of certainty into a world that will never stop flowing. The observer's prison. Why looking freezes the future forever. Stare at a candle flame and you'll notice a quiet tension in your attention, the urge to see it flicker the instant you fix your gaze. So here's the unsettling thought that slides in with the warmth. What if watching really can hold a system still, not by magic or willpower, but because looking is a physical act that changes what can happen next? Begin gently with the laboratory truth that hides behind the old proverb about a watched pot. Because in the quantum world, watching is not passive, it's a coupling. A tap on the system that writes a record somewhere, and that tap has a lawful consequence. It resets the system's story. The cleanest version is nicknamed the quantum Zeno effect, and despite the melodramatic name, its logic is disarmingly simple. Transitions take time to build. Not calendar time, but a small interval during which a system begins to shift from one configuration to another, and in that earliest interval, change grows only quadratically with time, which means if you keep asking the sharp question, "Are you still in the starting state?" fast enough, each check shoves the system back to yes before the shift, can gather momentum. Link enough of these resets, and the probability of leaving the starting state becomes tiny. So small that in the limit of absurdly rapid, ideal measurements, evolution out of that state is effectively arrested. This isn't philosophy, it's an engineer's tool. Early experiments on trapped ions and atoms showed that frequent interrogations suppress transitions that otherwise would have occurred, and modern versions use superconducting circuits or ultra-cold atoms to hold delicate states steady by watching them. But watching comes in flavors, and that's where the prison walls get interesting. A brutal, all-or-nothing measurement, the kind that slams a system into a definite outcome, can freeze a specific state, while a gentler, continuous monitoring can confine motion to a safe corridor, a strategy called quantum xenodynamics. Instead of pinning a system to a single point, you fence off a whole pasture, a subspace, and keep the animal from wandering out. This is already practical. In quantum information labs, repeated checks that don't reveal the value of a qubit still discourage it from straying into error states, and in atomic physics, repeated, non-destructive peaks can stabilize collective spins or keep atoms from tunneling into forbidden regions. In each case, the metaphor holds, but the details matter. You are not stopping time, you are reshaping the menu of futures by insisting on a question so often that only answers compatible with your question survive. The catch, the escape hatch, from the prison is that observation is a physical process with costs and side effects. So there's a complementary regime called the anti-Zeno effect, where frequent, sloppy or noisy probing can actually hasten change. Whether watching freezes or accelerates depends on the timescale of the environment's fluctuations and the sharpness of your interrogation. Watch faster than the system's own forgetfulness, and you suppress transitions. Watch at an awkward tempo that keeps nudging the system into resonance with noise, and you speed decay. This is why atomic clocks and precision sensors are designed with exquisite care about interrogation time and measurement strength. Probe too gently and you learn too little. Probe too often and you broaden the very line you want to resolve, like a photographer who overuses the flash and washes out the detail she came to capture. If you think all this is a quantum parlor trick with no echo in the large, look again at how information and control work together. Measurement by itself doesn't hold a classical object in place. Your ruler doesn't glue the ball to the table, but information enables feedback, and feedback can make a system behave as if the future were pinned. Optical tweezers hold a living bacterium in a beam of light and track its jitter. The tracking signal drives the trap to cancel motion, cold damping the particle towards stillness. Microcantilevers for force microscopy are watched and nudged in real time so their vibrations shrink to nearly nothing. None of this violates thermodynamics. You pay in energy to acquire, store, and erase information, and that cost keeps you honest. But it illustrates the deeper moral. Knowing isn't neutral. To know is to gain leverage, and leverage, used rapidly enough, can make the range of next states collapse to a narrow corridor of your choosing. Zoom back down to the smallest scales, and you meet a quieter prison you didn't choose. The environment is always looking. Molecules in air, photons from lamps, phonons in a crystal. Each is a tiny audience that monitors certain properties whether or not a human is present, constantly writing partial records into the world. This environmental monitoring, decoherence, doesn't freeze a particle in a unique value the way a textbook measurement does, but it does select robust pointer states that survive interaction, and once the environment has entangled itself with those stable properties, superpositions of them become exquisitely fragile. The result is a kind of natural Zeno. Macroscopic things hold their classical pose because the universe won't stop glancing at them. A dust grain in sunlight is measured millions of times per second by stray photons that reveal where it is, and those glances erase delicate quantum alternatives before they can grow. If you want quantum weirdness to last, you must hide it, cool it, isolate it, or even use versioned measurements that avoid learning the very property you're trying to protect. The art of non-demolition observation, which shows again that the prison is real but not inescapable if you are clever about what you ask. There's a beautiful piece of intuition beneath all this that you can carry without equations. Change requires coherence. Phases lined up, possibilities allowed. To interfere, and measurement broadly construed, is a coherence eater. Every time you extract a bit of definite information, you prevent some of those possibilities from working together. The way announcing a decision closes off the silent strategies you hadn't yet tried. In the short-time regime, where quantum systems haven't settled into exponential decay, that fragility is extreme, so rapid inspection keeps shattering the seed of a transition before it sprouts. Extend the idea, and you understand why some of the best error suppression techniques in quantum computing don't wait for mistakes. They pummel the system with rapid, carefully chosen pulses, or measurements, that average away the unwanted. Couplings, a cousin of Zeno that trades watching for rhythmic don't-go-there kicks. Do it right, and your qubit feels caged away from the noisy directions without you ever learning its secret value. If the title's phrase, freezes the future forever, still rings too absolute, temper it with the honest conditions. True freezing requires idealized, infinitely quick, perfectly sharp measurements that no real apparatus can deliver. In practice, you get a tunable break, not an off switch. There is also no magic shortcut to certainty, because the very act of looking that stabilizes one property necessarily scrambles its incompatible partner. Stare at position and momentum blurs, monitor energy tightly and timing goes fuzzy, and you must choose which prison to live in. But the practical lesson remains exciting rather than bleak. There is a slider you can move between openness to change and stability under scrutiny, and both nature and technology use it constantly. So end softly. With a human translation, you can try tonight. In your own life, attention behaves a little like measurement. It doesn't halt the world, but it does collapse your options for what you will notice and remember. Stare anxiously at an outcome and you can trap yourself in micro-loops that keep possibilities from developing. Look with curiosity at the parts you want to grow and check less often, and you give change room to cohere. In the lab, that's a recipe for holding atoms still long enough to compute. In a quiet room, it's a way to unfasten the feeling that the future is already fixed. The observer's prison is real as a physical principle and metaphor, but both come with a key. Choose your questions carefully and decide how often to ask them, because in a universe where looking writes the record, the cadence of your attention is one of the most powerful levers you have on what comes next. Nested realities. What if time exists only inside another simulation? Open your favorite game and pause it. The screen freezes, the music halts, but nothing inside the world knows it has been stopped. No citizen complains, no cloud protests, and when you unpause, their sun climbs again as if nothing happened, which is a strangely useful way to approach the question in this title. What if time, for us, exists only inside another simulation, not as a universal river, but as the progress bar of a higher-level process that can be paused, slowed, resampled, or branched without leaving an external bruise? Begin gently by noticing how time behaves in the simulations we actually build, because there it is never an ingredient of nature. It's a scheduling rule, and there are two big families of rules that already teach us how nested time might feel from the inside. In step-based models, the world updates in ticks, equal slices where all objects advance together, while in event-based models, the world jumps from one interaction to the next, skipping the empty stretches. In both cases, inside agents experience a seamless story despite the outer stop-start, because what defines their reality is not a metronome in the sky, but the order of interactions they can observe, a point computer scientists made concrete, with logical clocks that tell you what happened before what without consulting a wall clock. This is your first lesson in nested time. If you live inside a system, what you call time is really a record of consistent orderings plus a rule for prediction, and many different outer schedules can produce the same inner story. Push this further, and you see why relativity fits this picture so well without being a simulation claim. Physics already reduces time to patterns of comparison between processes. How many beeps of a cesium atom between two heartbeats? How far a pulsar rotates while a spacecraft coasts? And the laws are written so that those comparisons do not depend on who carries which clock. A simulator that respects only causal order and local rules can recreate such comparisons with no global ticker, which is precisely how distributed systems keep data consistent across far-flung servers. They enforce who can influence whom, and then allow each node to keep its own time, reconciling conflicts later. The inner residents never need to touch the scheduler to live their lives. What matters is that messages do not arrive before they are sent, and that predictions match observations within the noise they can measure. If you want to feel the strangeness of time inside time, look at how we render worlds. Graphics engines compute only what falls inside the camera's frustum at the level of detail the viewer can detect. Physics engines use constraints to solve for the next consistent configuration rather than integrating every sub-microstep. And networked games decouple the client's smooth animation from the server's authoritative tick by predicting, correcting, and blending. To the character inside the city, the wind blows continuously and the crowd flows, but the system beneath is a mesh of sparse updates, prediction, and patching, an existence built from correlations rather than continuous motion. Translate that intuition to a cosmic scale and you get a sober, testable thesis. If our time is inner time, it should be sufficient to describe the order of events and their lawful relations, and any global pauses or reschedules at the outer level should be operationally invisible so long as the correlations that define outcomes remain intact. Could we, from within, ever tell? You can design thought experiments that would leave fingerprints if the outer scheduler cut corners. Finite precision might produce tiny preferred directions or grain in the highest energy particles. Pseudo-random numbers might repeat with detectable periods. Expensive calculations might be faked by clever approximations that break under stress, or the universe might cull detail where no one is looking. The way a game lowers texture resolution for distant mountains. People have proposed concrete versions of these ideas, from looking for lattice-like artifacts in cosmic rays to scanning the statistical fine print of quantum outcomes for regularities. But so far, no robust evidence survives scrutiny, and the honest posture is to treat them as provocations for better measurements rather than as signs we have glimpsed the backstage. After all, in our own simulators, we can hide many of these shortcuts by using smarter algorithms, event-driven updates that guarantee exact conservation, cryptographic randomness that thwarts period hunting, error-correcting codes that make the inner world look cleaner than the hardware running it. There is also the brutal accounting question. Simulating quantum many-body systems naively eats resources at an exponential rate, so if we are nested, either the outer layer has physics we can't imagine, or it doesn't follow our rules when it computes ours, or it exploits structure inside our universe, sparsity, locality, symmetries, to compress the cost the way we compress video by exploiting the fact that most pixels don't change much between frames. None of these options is paradoxical, but all of them remind you that simulation is a hypothesis about descriptions, not an alibi for miracles. You still have to satisfy the same consistency checks we use on our own models: conservation, invariance, reproducibility. The most interesting payoff of thinking this way isn't a conspiracy theory. It's a clearer understanding of what time is doing for you. In a nested world, time is a bookkeeping device that lets limited agents coordinate predictions. It can flow at different rates for different subsystems if the scheduler gives them more or fewer updates. But those rate changes are detectable only via comparisons. Exactly how gravitational potential or motion alters clock readings. In real experiments, it can be paused from outside with no internal trace if the pause leaves no conflicting records. It can be forked into branches at a save point, but each branch becomes a self-sealed history, with no crosstalk, indistinguishable from a many possibilities, one outcome universe to its inhabitants. Even free will takes on a more practical meaning. You are free to the extent that the inner rules give you sensitivity to inputs and enough computational slack to evaluate options, not to the extent that you can climb out of your clock. If you want a clean, falsifiable way to use this perspective, treat it as a design philosophy for experiments and systems, rather than a claim about ultimate reality. Ask which conclusions depend only on observed correlations and which sneak in assumptions about an external schedule. Build clocks and protocols that compare processes directly rather than appealing to an imagined universal time. Borrow tools from distributed computing, logical clocks, consensus algorithms, fault-tolerant coding to harden your measurements against hidden rescheduling. And remember that the thermodynamics of information still binds you. Recording, transmitting, and erasing bits costs energy and creates heat, whether the world is nested or not. So even a perfect outer operator cannot give you inner miracles that violate that budget without altering the rules you've already measured. End softly with the human part of the thought experiment. If time is the scaffolding of our layer, not the spine of all layers, its value does not diminish. It becomes more like a contract, locally enforced, globally agnostic, that lets beings like us build reliable futures out of limited views. Seeing it this way makes you humbler about claims that outrun evidence and sharper about what you can control. Because nested or not, the only time you can spend is the one defined by your correlations and your choices. Keep those honest, and the world you inhabit, whatever runs beneath, will remain legible enough to learn from and generous enough to change. Deathless universes, a multiverse, where nothing ever truly ends. Stand with me at the graveyard of stars, white dwarfs cooling like spent embers, neutron hearts spinning down, black holes whispering away in radiation, and hold a thought that feels both audacious and oddly sober. Perhaps nothing in the universe truly dies in the ultimate sense, not because stones get up and walk or suns rekindle themselves, but because the most basic rule of microscopic physics is a promise that information is never annihilated, only scattered, scrambled, and woven into places you're not looking. Begin gently by translating that rule, called unitarity, out of jargon and into plain life. If you shred a letter and toss the pieces in a gust, you have not destroyed the words, you have dispersed them so widely and finely that recomposition is functionally impossible. And quantum theory says the universe plays that game perfectly. Its fundamental dynamics are reversible and length-preserving for information, which means every ending you witness is the conversion of a readable story into correlations spread across more degrees of freedom than you can control, not an erasure of the story's content. That principle sounds abstract until you test it against the most dramatic endings we know. The death of information in black holes, where Stephen Hawking's original calculation famously suggested that the thermal radiation a black hole emits carries no imprint of what fell in, as if the universe did sometimes burn books to pure ash. Yet a generation of work since has reversed that verdict. When you ask what the entanglement between a black hole and its radiation should do over time, it ought to rise, then peak, then fall again. The so-called page curve and modern calculations that include quantum corrections to the geometry reproduce exactly that behavior, implying that the radiation eventually carries out the fine-grained details in a form so scrambled you would mistake it for heat unless you knew the key. Even more striking is the Hayden-Preskill insight. Throw a diary into a very old, well-mixed black hole, and, after only a modest delay, the next bits of Hawking radiation already encode the diary's contents, hopeless to extract in practice, but present in principle, so what looked like absolute oblivion becomes a physics-level guarantee of return through correlations. This deathless character is not a loophole for magic, it's a discipline for bookkeeping. The no-hiding theorem says if information disappears from a system you can measure, it must have migrated into correlations with the rest of the world, meaning there is no legitimate, now you see it, now you don't. Only now you see it locally, now you must look globally, like a secret shared among many friends that none of them holds alone but all of them hold together. Step sideways, and the multiverse idea becomes less a carnival of copies and more a language for where information can safely live. In laboratory quantum error correction, you protect a single logical qubit by encoding it across many physical qubits so that even if some are lost or noisy, the content can be recovered. In a similar, mathematically precise way, certain holographic dualities map a gravitational bulk to a lower dimensional boundary code, where bulk information is redundantly represented in many overlapping boundary regions, and erasing some pieces doesn't erase the whole. This is not a verdict on whether our universe is literally a hologram, but it does teach a profound lesson about endings. When reality organizes information in error-correcting patterns, local catastrophes need not be global deaths. A star can collapse. A galaxy can drift beyond our horizon. A civilization can forget. And yet the fine-grained facts can be preserved in correlations distributed over larger domains than any one observer commands. Even a De Sitter-like universe, with a horizon, often painted as the stage for heat death, comes with a finite informational budget on that horizon, a kind of cosmic ledger that, while painfully hard to read, suggests that what fades from local view is still bookkept, somewhere physical rather than gone to metaphysical nowhere. This deathless posture isn't limited to gravity. In ordinary quantum matter, thermalization, the way a hot system forgets its initial conditions, looks like forgetting only if you insist on simple probes. A complex scrambler spreads the initial pattern across many body phases so that small measurements see bland averages, but complicated global observables could, in principle, reconstruct what was there. Interacting systems can even be coaxed to give back pieces of their past in controlled ways, as when scientists use echo, protocols and unscramblers to retrieve data that seems swallowed by chaos, concrete proof that seeming erasure often masks reversible dispersal. And at the border, where quantum turns classical, the universe performs a kind of information proliferation called quantum Darwinism. The environment doesn't merely decohere fragile superpositions. It redundantly copies robust facts, like the position of a dust grain into many environmental fragments, photons, air molecules, so that many observers can access the same record without disturbing it, which is why macroscopic facts achieve an eerie kind of immortality, while quantum details perish. The universe actively republishes certain information so widely that it becomes practically indestructible, not by law but by redundancy. If you hear nothing ends and think of overwrought claims about immortality, tighten the lens. The conservation at stake is not the persistence of bodies or the guarantee of happy outcomes. It is the deeper statement that the microscopic map from past to future is one-to-one, that probabilities add properly to one at every step, and that there is no authorized act of deletion in the language of the laws. Thermodynamics remains honest. The price of rearranging, reading, and writing information is heat released somewhere, and Landauer's principle quantifies that cost. So every attempt to compress, erase, or hide a message leaves a thermal scar. In that sense, endings are real as budgets, but not as voids. Even the bleak idea of a cosmological long silence is better pictured as a library whose shelves have been scattered into the wind than as a library that has been burned. The books are there as patterns in the air, but no one has the reach, patience, or precision to collect them again. Biology, seen through this lens, borrows its stubbornness from physics rather than defying it. Organisms die, yet lineages endure by copying description into new matter. Error-correcting codes in DNA preserve critical instructions across eons. Repair enzymes patrol and patch, and populations encode histories in gene frequencies and ecological structures. Information outlives its vehicles because selection and redundancy make it so. Culture pushes the trick further by inventing external memory, marks in clay, charges on disks, patterns in neural nets, so that meanings survive their makers provided someone keeps moving the patterns to fresh substrates. Each of these is a local rehearsal of the cosmic motif, endings for parts, endurance for patterns. What then of a multiverse where nothing ever truly ends? You don't need an infinite spray of disconnected bubble cosms to make the phrase meaningful, though such scenarios exist on some theorists' whiteboards. A humbler, testable reading is that the universe already behaves like a federation of overlapping codes and horizons, in which information rarely faces a single point of failure, destroyed here, preserved there, unreadable now, recoverable in, principle later, punishably expensive to reconstruct, but not lost from the ledger of what is physically real. Even the notorious philosophical spectre of quantum immortality misses the mark, because it trades in untestable personal continuations, whereas the honest content of deathlessness is impersonal. Amplitudes, correlations, conserved structures that persist whether or not any one observer follows them, so end softly with a posture that is both grounded and generous. To live in a deathless universe is not to be promised rescue from tragedy. It is to be invited to care about what you encode, facts, craft, kindness, because the universe will not casually delete them. It will scatter them, test them, and demand energy to preserve them, but it will also reward redundancy, error correction, and honest record keeping with a kind of durability that outlasts bodies and buildings. Your seconds are finite, your reach is small, but the patterns you set in motion can be made stubborn if you cast them into media that copy and protect. And that is the practical miracle the laws already allow. Nothing ends absolutely, so spend your time turning the fragile into the resilient and the local into the widely shared. And let that be your way of living in a cosmos where oblivion is a myth of convenience and conservation is the deeper, quieter truth. The Time Mirage. why the past and future might be the same place. Stand on a station platform at dusk and watch lightning strike both ends of a speeding train. From where you stand, the flashes seem simultaneous, but a passenger moving with the train swears the front bolt came first, and another, leaning the other way, is just as certain the rear bolt led. Already you've met the first hint of the time mirage, in a universe stitched into space-time. Past and future are not universal shelves, but different slices through one four-dimensional loaf, so that what you call before can be someone else's after, without either of you being wrong. Begin gently with that sober lesson from relativity. Events are locations like addresses, and each observer's motion picks a different way to slice the loaf into nows. Then let the idea deepen. If time is a direction in the same arena as space, with a different signature, but still part of the arena, the past and future are literally neighborhoods around you. The light cone behind that can send you messages, and the light cone ahead that you can still influence. And there, borders can swap roles under changes of viewpoint. The mirage sharpens when you look at the laws themselves, because the basic equations we use to describe isolated systems, Newton's rules for motion, Maxwell's rules for fields, Schrödinger's rule for quantum waves, work almost perfectly. Well, if you reverse the movie, and this time reversal symmetry says something radical in plain language, for every allowed pattern that carries you from state A to B, there exists an allowed twin that carries a time-reflected pattern from B to A. So the mathematics does not privilege past or future. What creates the felt arrow is not the core rules, but the boundary conditions and the way information is spread, which means that to a theory looking only at those rules, the place called past and the place called future are mirrors of the same underlying structure. To feel the difference between rules and boundary conditions, picture cream swirling into coffee. The molecules follow reversible dynamics, yet you never see unmixed cream leap back into a tidy pool. Not because the laws forbid it, but because, given the way the world started, with low entropy, orderly conditions, and the way you coarse-grain reality, ignoring the exact whereabouts of trillions of molecules, the microstates that would look like unmixing are fantastically rare. The arrow of time is thus a statistical bias born from a special beginning, not a demon carved into the laws, and if you knew every microscopic detail with infinite precision, you could, in principle, retrodict the past as reliably as you predict the future. Bayes works both ways when dynamics are reversible. So past and future are symmetrical inference problems on the same map of possibilities. In practice, chaos and noise make perfect retrodiction hopeless, but the principle stands, and you exploit it daily. Weather scientists run models backward to reconstruct yesterday's winds from today's pressure fields. Forensic engineers rebuild the moments before a bridge failed, and in astronomy, we deduce the past positions of planets by evolving the same equations in reverse. The success of those reconstructions whispers that the past and future live in the same mathematical territory and differ mainly in what data we choose to condition on. Electromagnetism offers a more exotic glimpse of the mirage. Maxwell's equations admit both retarded solutions, effects flowing outward from causes, and advanced solutions, waves that mathematically look like influences arriving from the future. In ordinary life, we choose the retarded ones because we set our boundary conditions that way. Radiation streams out from lamps to rooms, not from rooms into lamps. But the equations themselves don't flinch if you write the story with both, as in Wheeler and Feynman's old absorber idea, where the full, time-symmetric solution is picked out by the requirement that the rest of the universe absorbs radiation. Nothing supernatural follows, but the mere existence of advanced solutions is a signpost. The past-future split is a choice imposed by global conditions, not a ban in the math, and the same point reappears in particle physics through crossing, relations, where the same underlying amplitude describes either a particle going out or its antiparticle coming in, a formal way of saying that flipping who is before and who is after can be recast as the same interaction drawn differently. Zoom to the smallest scales and quantum theory adds a cautious but beautiful twist. You can condition your description on what you prepared and also on what you later found, pre- and post-selection, and make best-guess statements about what happened in between that are just as disciplined as predictions. When you do this, the best description of the in-between draws information from both temporal directions, a reminder that the most accurate story of an event is often a meeting point of constraints from behind and ahead. None of this lets signals travel backward or creates paradox because causality, the rule that usable influence never outruns light, still fences the field, but it does recast where the past and future live. They are not separate vaults. They are two ways of interrogating the same relational web, one by pushing forward, one by pulling back. Even our most familiar arrow, the thermodynamic one, can be seen as a perspective effect when you change the questions. If you ask about fine-grained microstates, the volume they occupy in the space of possibilities is preserved step by step. No real expansion, no contraction. So nothing about the flow distinguishes yesterday from tomorrow. The arrow appears when you compress details into macrostates, and when you place a low entropy pin in the map called the early universe, a special boundary that funnels probability flows so overwhelmingly toward higher entropy that it drowns the symmetric options in practice. Change the pins and you change the apparent direction, which is why a refrigerator can pump heat from cold to hot as long as you feed it electricity. Locally, the arrow tilts because you supply a different boundary condition at the plug. If you want a tangible picture of past and future might be the same place, stop thinking of time as a road and think of it as a coordinate on a chart. The place is the state space of the world, and trajectories are lines on that chart. Predicting and retrodicting are simply tracing the same line in opposite directions, with different pieces of the line revealed. Your sense that one of those directions is the real one comes from how memories and records are laid out. Records point backward because making a durable mark increases entropy, so the universe naturally stores evidence of what has already happened and almost never of what has not. But that asymmetry is about storage, not about the deep geometry of the map. The past and future are overlaid on the same canvas, colored by what you know. What you should take from all of this is neither cynicism nor mysticism, but a more precise humility. The deepest parts of our theories treat before and after as different coordinate choices on a common structure. The arrow you live by arises from low entropy beginnings, from how information spreads, and from what questions you ask. When you plan, you are pushing constraints forward. When you explain, you are pulling them back. In both cases, you are navigating the same landscape, and softly with the practical gift hidden in the mirage. If past and future share a place, then the way to enrich tomorrow is to change the constraints you set today. Write honest records, preserve gradients that let work be done, build systems that keep options open, and you'll find the future tilts in predictable ways, not because you outran time, but because you shaped the map that both directions must follow. Quantum Omniverse, where every possible history already exists. Imagine you flip a coin and it lands heads, but the itch you can't scratch is this. The equations you used to predict the toss never included a command that says, choose heads. Now, they only said how possibilities evolve and combine, linearly and without favoritism. So what if the most straightforward reading of those equations is that both outcomes continue, with you entangled to the head version in one strand of the story and to the tail version in another? Begin gently with the core proposal behind a quantum omniverse, not as fantasy, but as a disciplined hypothesis. The wave function, the mathematical object that captures what can happen, never actually collapses. It keeps unfolding according to one simple rule. And when a measurement-like interaction occurs, you do not force a single result. You become part of a larger superposition where each outcome is paired with an observer who sees it. The reason those observers feel alone is decoherence. The measured system, the device, the air, and your nervous system quickly share telling traces of the result, and those traces leak into countless environmental degrees of freedom so fast that the different outcomes cannot interfere with each other anymore. From within a branch, you experience a clean, classical-looking world, because every available record in your surroundings agrees with itself, not because alternative outcomes were annihilated. In this sense, every possible history already exists means something precise and limited. Every history with non-zero amplitude that is consistent with the dynamical rules and the actual conditions proceeds in parallel, while those with zero amplitude never occur, and wildly inconsistent stories, violating conservation or the structure of interactions, aren't in the menu at all. So the Omniverse is not a license for anything goes fiction. It is a commitment to keep every lawful possibility alive until and unless dynamics themselves forbid it. Push a layer deeper, and two questions arrive together. What exactly counts as a history, and where does probability come from if all of them occur? A history, in this careful usage, is a coarse-grained sequence of stable records, pointer-like facts that remain robust under further interactions, stitched into a narrative by the environment's habit of copying those facts widely. Once such, a record forms. Interference between macroscopically distinct alternatives becomes fantastically unlikely, because you would have to erase or reverse those copies everywhere to reunite the strands, which is why branches behave like independent worlds for all practical purposes. Probability, then, is not a wheel of fate that picks one world to be real. It is a weight that tells you how thickly each branch runs through the space of possibilities, and our best derivations of that weight recover the familiar rule that frequencies are given by the square of the amplitude. Some arguments lean on symmetries of entanglement that make different ways of slicing the joint state give the same betting odds. Others lean on decision theory to show that a rational agent inside the framework should care about branches in exact proportion to those weights. Not everyone agrees these arguments close the case, but they shift the puzzle from why do probabilities exist to why should we treat branch weights as the right guide, which is exactly what a predictive science needs to do. What about evidence? How could a view that keeps all outcomes be anything more than a story? The honest answer is that the many-branch picture predicts the same statistics for experiments as the usual collapse story, so you test it indirectly by testing the pieces it relies on. You isolate larger and larger objects and watch coherent superpositions survive longer. You engineer macroscopic devices, superconducting circuits, ions, even big molecules, that show interference when protected and lose it when they leak information. You build quantum computers that choreograph huge families of computational paths, and then let them interfere so that only answers compatible with the algorithm remain amplified. This is sometimes sold as parallel universes doing your math, which is more poetry than fact. But the core is fair. You arrange many possible histories in such a way that, before decoherence, they can still talk to one another through interference, and you shepherd that interference so it cancels the wrong answers and boosts the right ones. A tangible demonstration that unrealized alternatives have causal bite before records lock them into separate fates. At the cosmic scale, the Omniverse idea intersects with another, eternal inflation, a mechanism that seems to produce an endless froth of expanding regions with different broken symmetries and maybe different effective constants. If both mechanisms operate, inflation seeding many big stage environments and quantum branching playing out within each, then every possible history spans two axes, one across landscapes of laws, another across outcomes within a fixed law set. But here, caution matters, because possible must be disciplined by measure. In an inflating cosmos, volumes and counts can blow up to infinity, and naively asking what fraction of universes look like ours becomes meaningless unless you define a way to regulate and compare. Similarly, not every microhistory has appreciable weight in the quantum sense. Amplitudes funnel probability towards some patterns and away from others, and no one should claim that every logically imaginable narrative occurs somewhere. The Omniverse, if real, is carved by dynamics and by initial conditions, not by wish. A natural worry follows the wonder. If other branches contain other U's, does anything you do matter? Inside the framework, the practical answer is yes, in the same way probability has always mattered. Your choices affect which subbranches grow thick and which thin out for the observers who will inherit your name tag. When you reduce noise in an experiment, you tilt weight toward branches where a delicate effect is seen. When you take precautions, you move amplitude from injury branches to safety branches. You cannot message your twins, and you cannot salvage weight from branches you neglect. So the ethical posture that emerges is surprisingly familiar. Behave as if outcomes with higher weight are more likely for the people who come after you. Because that is literally what the theory says. The romance of all paths happen doesn't trivialize risk, it quantifies it. Two more clarifications keep the story honest. First, decoherence is not a metaphysical guillotine, but a physical process with a timescale and a basis that depend on context. What looks like a split to you might look like a coherent superposition to a larger, colder, more isolated apparatus. And in principle, one could contrive quantum eraser-style setups that reunite carefully protected alternatives, proving that branches are approximate structures that become real for agents with limited reach in noisy worlds, not engraved partitions in a cosmic ledger. Second, already exists should be read as is present in the universal state now, rather than was laid down at the dawn of time, because the branching structure grows as interactions proceed and records proliferate. What is present to a late-time description includes a vast tree of correlated outcomes that were once delicately coherent possibilities and are now effectively separate books on separate shelves. Where does this leave you? Sitting in a quiet room with a coin in your palm and a lifetime of choices in your pocket. Not paralyzed by metaphysics, but sharpened by it. The Omniverse, taken seriously, tells you that reality is richer than a single track without turning truth to mush. It tells you that evidence lives in the patterns of interference and the stability of records, not in whispers from other worlds. It tells you that possibility is not permission, it is responsibility, the responsibility to prepare states and contexts that make good branches thick and bad ones thin. And it suggests a gentler humility toward uncertainty, because beneath your ordinary odds lives a structure where outcomes are not picked, but weighted, and your role is to nudge those weights with care. End softly here. If every lawful history already exists in the only sense that matters to physics, then what you call the future is the set of branches you have not yet read. And what you call meaning is the influence you exert on which of those pages your successors will inhabit. Whether or not you ever see your twins, you share with them the same rulebook and the same chance to leave thick, honest traces, and that is enough to live by. Undying signals. When information refuses to age or decay, listen for a message that refuses to fade, the kind you can send across noise, years, and even changing substrates, and hold the unsettlingly practical idea that some signals aren't merely long-lived, they are engineered or protected so that, in all the ways that matter, they do not age. Begin gently with a pulse of light in a glass fiber that ought to spread and smear, because dispersion makes fast parts outrun slow ones. Yet if you shape that pulse just right, the fiber's non-linearity pushes back and the two effects cancel, leaving a solitary hump that travels for hundreds of kilometers without losing its face. A soliton. A wave that carries its own repair kit. An equation's way of saying, I will not blur. And this is your first template for undying information. Structure that rides symmetries and balances so changes average to zero. Zoom from fibers to materials where edges themselves protect what moves. In a topological insulator or a quantum Hall system, electrical current flows along the boundary in channels that are immune to small scratches and grime, because the number of boundary modes is tied to a global winding count you cannot change without tearing the whole band structure. As long as the environment nudges gently, backscatter is forbidden and the signal refuses to degrade, not because the electrons are brave, but because mathematics has locked their path with an integer. The principle generalizes in breathtaking ways. Encode a bit non-locally, spread across a whole medium so no local poke can read or flip it, and you get topological order. What future quantum memories hope to use with exotic excitations, whose braids, not their locations, do the talking? Here, information is undying because it is nowhere in particular, and thus cannot be spoiled in one place. But undying isn't only about topology, sometimes it's about not joining the crowd. In many body localization, strong disorder can keep a quantum system from thermalizing, even when interactions are present, preserving a fingerprint of the initial state for arbitrarily long times. Where ordinary materials share energy until all memory dissolves into temperature, these disordered lattices hoard memory in local integrals of motion. A stubbornness so strong that experiments can write a pattern and come back later to find it's still legible, proof that under the right conditions, forgetting is optional. Cousins of this phenomenon appear in integrable systems, chains with infinitely many conservation laws, where information sloshes rather than diffuses, and in pre-thermal regimes, where drives are fast enough to trap a system near a quasi-conserved quantity for millions of cycles. Even time crystals, a phase where a driven system ticks at a rhythm different from the one you are beating it with, derive their longevity from this kind of protected near conservation, a metronome that refuses to drift so long as the drive remains within guardrails. Signals also refuse to age when you store them in modes the world barely touches. High-Q optical and microwave cavities recycle light or microwaves for billions of oscillations. Whispering gallery resonators the size of a grain of sand-trap photons that circle with vanishing loss. Superconducting loops let currents flow for hours without resistance, and at a cosmic scale, neutrinos and gravitational waves propagate across the universe with almost no scattering, slipping through matter that would erase radio or light, so that a burst from a collapsing star or the merger of black holes arrives. As crisp as conditions allow even after traveling for eons, if you need a second recipe for undying, here it is. Choose carriers that barely interact with their environment, so there is nothing around to steal their story. Still, the most powerful way to make information age-proof is to admit that noise is inevitable and designed so it doesn't matter. Shannon showed that for any noisy channel, there exists a coding scheme that drives error as low as you like, provided you add enough redundancy and decode wisely. Modern space missions speak to us across light hours using low-density parity codes and turbo LDPC families that scatter each bit's identity across thousands of checks, so that even if cosmic rays flip pieces and antennas hiss, the message can be pulled back together. Your photographs on a decades-old disk rely on Reed-Solomon codes that can reassemble the picture even when entire blocks are scratched away. Solid-state drives scrub themselves, reading and rewriting data to heal silent bit rot before it accrues. In quantum labs, surface codes catch and fix stray flips not by peeking at the qubit's value, which would destroy it, but by measuring parity constraints around it, so the logical information survives indefinitely as long as you keep feeding. The correction loop, an active immortality purchased with energy, sensors, and math. Notice the pattern. Undying signals either hide in symmetry, hide in isolation, or refuse to hide at all, blazing themselves in many places so no single failure can erase them. There is a subtler kind of immortality that shows up when you choose the right observables. Some quantities simply do not flow with time because a symmetry forbids it. Total charge in a closed circuit, total momentum in free space, and when you express your message in that conserved language, it becomes immune to aging so long as the symmetry holds. Physicists exploit this when they encode standards, like the second or volt, in atomic and quantum invariants rather than in aging artifacts. Engineers do the same with cryptographic hashes and signatures, which are not physical conservation laws, but mathematical ones. Tamper with a block of data, and the signature ceases to match. So the truth of the file, as defined by the scheme, does not quietly decay. Pair that with good archival practice, multiple geographies, different media, periodic refresh, and you can make cultural memory behave more like a conserved charge than like a fading ink. If the phrase refuses to age sounds like hubris, temper it with the honest costs and limits. Solitons need careful power and dispersion management. Topological channels protect against small local insults but not against global rearrangements that change the invariant. Localized phases lose their grip when the environment couples too strongly. High Q resonators betray you if tiny losses add up. Error correction works only if noise stays below a threshold and if you keep paying the energy bill. Even neutrinos redshift with the expansion of space. Undying is never free. It is a trade. Symmetry for flexibility, redundancy for storage, isolation for accessibility, active correction for power. Yet the trade pays off so reliably that make it undying has become a design stance, not a miracle. And there is a philosophical dividend tucked inside the engineering. When you realize that information can be made more durable than the material hosting it at any one moment, you start planning your own signals differently. What you want to. Last you express in invariants, clear definitions, open formats. You scatter across diverse carriers, paper plus cloud plus tape. You choose channels with weak coupling to chaos, plain text ages better than proprietary binaries, and you schedule periodic rewrites so entropy bills are paid before they come due. That is not poetry. It is the same logic a soliton or a topological edge uses, translated into human craft. End softly with the thought that in a world where most things crumble, the refusal to age is never an accident. It is built from symmetry, choice of carrier, and the humility to admit noise and then outsmart it. And that means the signals you care about can outlive you honestly if you design them to, not by denying physics, but by letting its deepest habits do the keeping. Frozen future paradox, a tomorrow that already happened. Stand beside a glacier and read the odd placard a caretaker might hang there, tomorrow installed years ago, and let the sentence work on you, because the frozen future paradox isn't a prophecy about fate so much as a map of places in nature where the range of tomorrows has already narrowed to a single corridor, not by magic, but by the way patterns overwhelm details. Begin gently with a truth you can test in a kitchen or a lab. If you push many different fluids, broth, oil, molten metal, close to their boiling or mixing thresholds, their flicker and swirl share the same exponents and textures. And that sameness isn't coincidence, but universality. The rule that when countless tiny ingredients jostle under the same symmetries, the only future that survives coarse graining is the one those symmetries allow. It means that once a system wanders into the right neighborhood, most of what could have made next week different has already been erased, and what remains is a fixed set of outcomes that every material, every run, obediently approaches. This is the first honest sense in which tomorrow already happened. The large-scale script is written by invariants and fixed points, not by the trivia of initial jitters. The same quiet lock appears in the way flowing matter forgets. After a brief, messy transient, wildly different initial splashes relax toward the same hydrodynamic attractor, so pressure, temperature, and flow obey the same equations with the same constitutive relations regardless of how the chaos began. Engineers rely on this to design nozzles and turbines, and even nuclear physicists see it when fireballs made in particle colliders settle into fluid-like behavior astonishingly fast. Once you are on the attractor, tomorrow's bulk motion is already scripted by conservation laws and geometry. A frozen future in the practical sense that small perturbations only wobble the same curve. Shift your gaze to the sky and the theme turns cosmic. In an expanding cosmos with a persistent push from dark energy, the cosmic no-hair idea says that most wrinkles in the fabric, tilts, shears, local peculiarities, are ironed away as space stretches, and the large-scale future tends to a featureless, de Sitter-like hush with a steady bath of horizon noise. Galaxies you can still see today will slip past a boundary you can never reach. Starlight will redshift beyond your instruments, and within your gravitational island, the menu of new large-scale structures closes out. No alarm will ring, but the far future sky has, in a sober sense, already chosen its look. because the equations direct almost every initial condition toward the same simple attractor. This is not doom, it is geometry. A funnel in phase space that takes many beginnings to one end. Now bring the lens down into statistics, where frozen stops sounding mystical and becomes everyday. When you gather a huge crowd of microscopic actors, air molecules in a room, electrons in a wire, the law of large numbers and its sharper cousins say that macroscopic quantities will land in a narrow band around their typical value, with odds so overwhelming that deviations of practical size can be treated as forbidden. Your room's pressure tomorrow afternoon, absent a storm or a heater, is already known within a tiny tolerance, because there are unimaginably many microstates that look like normal and vanishingly few that look like weird, and the system wanders almost exclusively among the typical ones. That's the working meaning of a tomorrow that already happened. Not that the exact micro-arrangement is fixed, but that the macroscopic description has collapsed to a tiny slice of possibility space long before the calendar page turns. The quantum story adds a subtler layer that is easy to misread. If you specify the exact state of a system today, a heroic if, the theory fixes the weights for every possible outcome tomorrow. Nothing in the dynamical rule picks a single result in advance, but the distribution of results, the odds you should bet on, is already set. A frozen ledger of amplitudes that will not change until you interact. Inside many-body quantum matter, there's a stronger claim called the eigenstate thermalization hypothesis, which says that for practically all high-energy states, the expectation values of simple observables already match thermal values, so subsystems look equilibrated even without literal mixing. You can watch this in cold atom experiments where a complicated cloud relaxes to textbook predictions, not because the universe rolled loaded dice that day, but because almost every microstate with that energy looks thermal to any small probe. The future for your thermometer is pre-decided by typicality, and yet, to keep your skepticism alive, learn the exceptions. Integrable chains carry infinitely many hidden constraints and relax not to a simple temperature, but to a generalized ensemble determined by all those charges. Disordered lattices can many-body localize, trapping information and preventing full thermalization. And rare quantum scars carve bright, long-lived stripes through the space of states where dynamics revisit special patterns instead of melting completely. These counterexamples don't kill the paradox, they sharpen it. Tomorrow is often frozen by symmetry and typicality, unless structure smuggles in a protected memory. Biology writes the same lesson in flesh. A fertilized egg contains a regulatory network and a landscape of attractors so that, as morphogen gradients spread and genes toggle, cells roll downhill towards stable fates, neuron, muscle, skin, much the way a marble finds a basin. Developmental biologists draw this as valleys in an epigenetic landscape, and the point is not that every individual's form is identical, noise and environment matter, but that the space of viable futures is discretized into a handful of robust endpoints. Once certain thresholds are crossed, once particular transcription factors are high or low, the rest of the program is largely constrained, and tomorrow, for that cell type, has in essence happened. This isn't fatalism, it's design. Evolution builds organisms that reach the right fates reliably by making wrong fates hard to access. Information theory gives you the engineering, twin, if you choose a code and a decoder that sit below a channel's noise threshold, then for messages of sufficient length, the error rate plunges exponentially with block size. In practice, a deep space photo stored with strong redundancy has its tomorrow frozen at the moment of encoding. Barring catastrophic failure, later noise can be corrected away, and the image you will reconstruct next year is already determined by parity checks baked into the bits today. You can flip this to finance and forecasting too. When a system is ergodic and you have enough data, your best predictor for tomorrow's mean is today's, and adding more memory doesn't move the needle. There isn't mystery in that plateau. only the arrival at a regime where the remaining uncertainty is sampling noise. But if you stop here, you miss the living edge where frozen and fluid meet. The very structures that lock in tomorrows also draw basins with switchbacks where a timely nudge changes which fix point you will inherit. A climate system with multiple stable patterns, monsoon on or off, ice sheet, large or small, can sit near a tipping point where small forcings commit it to a different long-term state. A brain network on the verge of a decision amplifies weak biases into actions that close doors and open others. A material, cooled through a phase transition, chooses one of several equivalent patterns, and tiny seeds can decide which symmetry breaks. The paradox lives precisely here. Within a basin, tomorrow looks pre-written, but which basin you end up in remains exquisitely sensitive to preparation and intervention. What feels like fate from inside a valley looked like choice at the ridge. End softly by recasting the phrase that brought you in. A tomorrow that already happened is not a supernatural spoiler, but a statement about where the world's equations and statistics squeeze. Freedom into form, in attractors, typical sets, conserved quantities, and robust codes. Tomorrow's macroscopic outline is negotiated long before the clock strikes, and your power is not to rewrite the outline from within, but to steer which outline you'll inherit. By choosing initial conditions with care, by identifying and using the levers of symmetry and feedback, and by acting early enough to cross into a better basin. Accept that much of the future is frozen at the level of patterns, and paradox dissolves into strategy. Learn the patterns, find the thresholds, move while movement still matters. Dimensional spillover. Could time be leaking from another reality? Imagine discovering that the rhythm you live by is not entirely your own, like feeling a faint draft under a closed door and realizing, with a chill of curiosity rather than fear, that another room must be there. So ask the question cleanly. Could time in our world be a spillover from a deeper reality? A pace imposed or flavored by dynamics outside the slice of universe we can touch? Begin gently with the least sensational version scientists actually study. The idea that our familiar three-dimensional space might be a membrane, a brain, floating in a larger bulk, where at least one extra dimension exists, and that while ordinary matter and forces are pinned to our brain, gravity is allowed to wander. If that bigger stage has its own clock, its own way of ordering events, then our measured time could be the projection of bulk change onto our surface, the way the shadow of a moving gear looks like a hand sweeping a dial, and any leakage would not be people falling out of Tuesday but small disciplined departures in how clocks, gravity and light behave. What would such spillover actually look like to you, sitting with a watch and a telescope? First, gravity might fade with distance a little faster or slower than the inverse square rule predicts if part of its field lines bulge into the bulk. Laboratory torsion balance experiments have probed millimeter and submillimeter scales, hunting for such deviations, and astronomical measurements test them on galactic scales, because leakage changes the way galaxies hold their stars and the way the universe's expansion accelerates. Second, gravitational waves could lose amplitude more quickly with distance than light does, as if some of their energy oozed into the extra dimension. Standard siren observations compare the brightness of a distant smash-up in gravitational waves with the light from its partner explosion to check for just that mismatch. Third, you might see apparent bookkeeping quirks. Energy that seems to go missing in 4 dimensions could in fact have flowed into the bulk through gravitational degrees of freedom, a loss you'd infer only statistically by how structures evolve, or by how precisely balanced systems slowly drift. None of these ideas gives permission for paradox. Causality, the rule that usable influence never outruns light along allowable paths, still fences the field, but spillover would mean our fence posts are mortared into a deeper wall. There is also a quieter route to the same question that has nothing to do with extra directions in space. Perhaps time, in the sense that matters for prediction, is not a master variable at all, but a clock we assemble by comparing processes, and part of what we call our clock could be slave to rhythms, in a hidden sector that only talks to us weekly. Picture a cosmic metronome, a field that oscillates or drifts so slowly that it's almost frozen, coupled faintly to the ingredients of atoms. If that field wavers, the energy gaps in atoms would wobble too, and the second defined by those gaps would breathe with it. This is not idle speculation. Networks of optical clocks in laboratories already compare their ticks at astonishing precision, watching for correlated drifts that would betray an ultralight field permeating the galaxy, and also for sharp, transient glitches that could be the signature of a dark sector domain wall sweeping through. No such signals have stuck, but the hunt is a crisp way to ask whether some other reality's gentle motion tugs on our units. A cousin of this test asks whether fundamental constants, like the strength of electromagnetic interaction, drift over years or across the universe. If a hidden sector leaks into ours, slow changes could be imprinted in those numbers. Astrophysical, spectra from ancient light, and meticulous atomic comparisons on Earth have boxed such drifts into nothingness at extraordinary precision, telling us that if spillover exists, it is very shy. Another family of clues would come from the symmetry that keeps physics the same in all directions of space and time at small scales. If leaked time introduced a preferred frame or tempo, exquisitely clever Michelson-Morley descendants, particle ring experiments, and high-energy cosmic ray observations would see it as an anisotropy, a different speed limit, or an odd energy threshold. The fact that these tests keep returning no preferred frame here doesn't kill the idea, but it corrals it. Any extra reality must respect the local democracy of directions we observe, or couple so softly that only next generation instruments can hope to catch it. There are also gravitational ways to look for the draft under the door. Relativity insists that gravitational waves and light share the same cosmic speed to extraordinary accuracy. If time were seeping in from a bulk that lets gravity take shortcuts, you might catch a consistent lead or lag between a wave and its light counterpart, or spot frequency-dependent dispersion that the simplest theory forbids. Similarly, if part of a wavefront leaks, the distance inferred from its amplitude would disagree with the distance inferred from light in a way that grows with how far it traveled. An observational pattern you can check again and again as the catalogue of cosmic events grows. And then there is the most conservative translation of spillover, which is not about shape but about bookkeeping. In open quantum systems, the rule for any small piece of reality immersed in a larger one, the arrow of time you feel arises from entanglement with the environment, whose degrees of freedom play the role of an external sink for coherence. If the environment includes vast hidden sectors, or even other brains, then our sense of direction and our rates of decoherence are, already in a profound but testable way, borrowed from outside. You can test aspects of this by isolating systems so carefully that their environment stops dictating the arrow, letting tiny islands of matter run backward, looking interference or sustain fragile superpositions long past what a warm world allows, and by seeing whether gravity itself acts as a special decoherer, an observer with a unique accent that could hint at bulk connections. To keep the story honest, line up the policy limits. Nothing in the sober versions of this idea allows messaging with the past, staging paradoxes, or flipping personal time by will. If spillover is real, it must respect the conservation laws and symmetries we have measured to absurd precision, or announce itself in carefully patterned failures that repeat across independent experiments. Most current tests tell you that if there is a deeper room next to ours, its drafts are faint. The inverse square law holds down to sub-millimeter scales. Gravitational waves keep time with light within tight bounds. Clocks separated by altitude and motion agree once you correct for relativity to jaw-dropping decimals, and searches for drifting constants mostly come up empty. Yet the absence of drama is itself instructional, because it transforms a fanciful question into a design brief. If time leaks, here is exactly how it would show up, and here are the knobs we must tighten to see it. The philosophical payoff is quiet but bright. Imagining dimensional spillover doesn't mean shrugging off rigor. It means asking better, more operational questions about what time really measures. It pushes you to define seconds by invariant comparisons, to build clock networks that can notice a shared tug, to use gravitational messengers as rulers for space and time, and to be suspicious, in a productive way, of anything that depends on a universal schedule no one can check. End softly with the image you started with. A closed door that may open onto nothing more exotic than an empty hall, but whose faint draft has already made you better at keeping time. Whether or not another reality's clock brushes ours, the act of looking, carefully, humbly, with instruments that translate wonder into numbers, leaves you with a truer sense of the rhythm you actually live by. Silent Big Bangs. Universes that begin without ever starting. Imagine a dawn with no sunrise, a day that brightens because the night quietly changed its rules rather than because a star cracked the horizon. That's the feel of a silent Big Bang, a universe that begins without ever having a first bang-like instant, not by dodging physics, but by asking it to describe a beginning as a boundary condition, a phase change, or a rounding off where the very idea of before stops being meaningful. Begin gently with the proposal that at the earlier scales time itself may have been the wrong concept, so the universe didn't start at a point but rounded in from a region where time behaved more like a spatial direction, and the geometry was smooth, leaving no sharp edge to bang against. You can picture it like the tip of an ice cream cone that has been sanded into a dome. There's a surface you can walk on, equations you can write, but no corner that counts as a first tick. In such no-boundary style pictures, the laws don't narrate a spark. They assign weights to entire self-contained histories. And the classical world you know emerges where those histories have the largest weight and the smallest quantum jitters. A different quiet beginning is tunneling, where a universe can appear the way a particle sometimes shows up on the far side of a barrier without crossing it in the classical sense. The barrier is not empty space, but the classically forbidden region of geometries, and nothing means no classical space-time, not metaphysical void. Once through, expansion lights up and ordinary clocks switch on, so the first frame you could live in already contains a running cosmos, the way a movie can open on the second scene without showing the first cut. There are also emergent universe ideas that replace the bang with a long, quiet prelude, an almost static, gently humming cosmos that, through a subtle instability, glides into accelerated growth. Imagine a lake so still you'd call it timeless, then watch as a barely perceptible breeze organizes ripples that grow into waves. That shift, not a crack of thunder, is the beginning. Yet another silent route is the ekpyrotic story, in which ultra-slow, smoothing contraction sets initial conditions so clean that a later bounce or collision yields a hot expanding phase without a past singularity. Here the bang is an interface between regimes, like two sheets of ice sliding and releasing heat where they meet, more handshake than explosion. String-inspired pictures add their own hush by letting the early universe be filled with strings and brains whose thermodynamics and dualities prevent singular crushes. So again, the transition to expansion is a change of phase, not a detonation. What would make any of these honest science rather than graceful metaphors is evidence. And the wonderful thing is that silent doesn't mean undetectable. A universe that rounds off instead of cracking usually predicts particular patterns in the tiny ripples of temperature and polarization across the microwave sky, including distinctive low multipole features or a capped amplitude for primordial gravitational waves. An ekpyrotic smoothing phase tends to produce a very faint blue-tilted background of gravitational waves rather than the red-leaning spectrum often associated with standard inflation, and it imprints a specific style of non-Gaussian correlations. In the primordial density fluctuations, subtle 3-point and 4-point fingerprints that new satellite maps and ground-based telescopes are designed to hunt. Emergent universe models can leave hints in the spatial curvature or a slight running of the spectrum's tilt, where a perfectly scale-free pattern gives way to a gently bent one. And if the opening move involved brain interactions, you might find relics like thin line-like discontinuities in the sky's pattern from cosmic strings, revealed by sharp lensing effects or by small steps in the microwave background. Noisy threads in an otherwise placid weave. Farther ahead, 21-centimeter cosmology will map the hydrogen fog of the universe's dark ages and could expose delicate features of the earliest sound waves that different beginnings imprint in different ways, while a global network of atomic clocks tuned to sniff for correlated planet-spanning jitters could catch a whisper from an ultralight field that helped set the initial conditions. Even gravitational wave standard sirens, distant black hole or neutron star mergers, double as rulers of the cosmic expansion, and can stress test whether our early time assumptions mesh consistently with late time distances, which a truly silent start must pass without excuses. To keep the conversation honest, you also need to reckon with no-go results and semantics. Some theorems suggest that any universe that has been expanding on average must be incomplete to the past in a particular technical sense, which doesn't kill silent beginnings but corrals them. They must either be past eternal without average expansion for a long stretch, the loitering prelude, or stitch our expanding patch onto a different regime, the rounded cap, the bounce, the interface, where time as you use it is simply not the right yardstick. And when you hear tunneling from nothing, police the word nothing, it's not a claim that existence pops from true philosophical non-existence. It's a statement that the mathematical object we evolve, a wave function on the space, of geometries and fields, assigns non-zero weight to histories with small, closed spatial slices, even when no classical space-time existed to host a before. Likewise, no boundary does not prophesy predestination. It tells you how to set the boundary conditions for the entire history at once, the way the shape of a soap film is fixed by its supporting wire rather than by any sense of when the soap started to flow. If you want an intuition you can rehearse in your hands, look at phase changes and the way the world's seeds structure without a crack of thunder. Cool a metal or a superfluid past a critical point and the Kibble-Zurek mechanism sets how many defects appear based on how fast you cross, not on a bang-like impulse. Quench a Bose-Einstein condensate and watch particles appear from ripples in the order parameter, the way cosmological particle production would from a changing space-time. No explosion, just a parameter sliding past a threshold that turns the vacuum into something with excitations. Even in optics and fluids, horizons can be mimicked and their analog Hawking radiation teased out, reminding you that the birth of quanta can be a quiet rearrangement of background conditions. If the cosmos began by crossing such a threshold, its first act was a whisper of amplified fluctuations, not a clap. The arrow of time in a silent start comes from the same place it always does: special conditions and the growth of entanglement. Only here, the special is enforced by the way the beginning is posed. Rounding off promotes smooth, low-complexity configurations. Slow prelude or ekpyrosis crushes wrinkles and anisotropies. Tunneling picks compact, simple geometries with high weight. From any of these, complexity and entropy then race outward as interactions knit subsystems together. So the quietest beginnings can still explain a loud present, and there is no need to pretend the arrow is an illusion. In fact, modern work on computational complexity in quantum systems gives you a complementary picture. Start from a very simple initial state and let the circuit that builds the universe run. Complexity grows for an astronomically long time, and that growth is as arrowed as any thermometer's climb toward equilibrium. A silent start is simply a choice of a low complexity origin, not a claim that the subsequent story lacks drama. All of this is testable in the sense that it must fit a web of constraints. Nucleosynthesis yields, the detailed map of the microwave, background, the distribution of galaxies, the absence or presence of particular gravitational wave backgrounds, and the web tightens every year. If a model requires a level of primordial gravitational waves that experiments keep failing to see, it must adapt or go. If it predicts a kind of non-Gaussianity, the sky refuses to deliver, it recedes. If it leans on a small positive curvature, new surveys can confirm or squeeze it. Silent does not mean slippery. End softly with the thought that beginning without starting is not an escape hatch from explanation, but a sharpening of the question, what had to be true so that a world like ours could unfold? Sometimes, The answer is a rounded cap instead of a corner, a threshold crossed instead of a spark, a prelude that sets the key so the symphony can erupt on its own. Either way, the music you live in is real, and the way to honor it is to keep listening for the faint signatures that remain from the first quiet bars. The Great Clock Mismatch: Why the Universe Can't Agree on Now. Try this experiment in your mind. Task every clock on Earth, from wristwatches and radio beacons to the hydrogen masers steering deep space probes, to clap at the same instant, and you'll discover why the universe can't agree on now. Not because we're sloppy timekeepers, but because the rules of space-time themselves won't let a single, universal present exist. Begin gently with how you'd even try. Einstein's synchronization uses light signals and a convention that two distant clocks are together if a ping sent from A reaches B and the reply takes equal time on the way back. But that rule only works cleanly in an unaccelerated, non-rotating frame. Put your clocks on a spinning planet and you hit the Sagnac effect. A tiny but inexorable offset that means a light pulse going east and the same pulse going west do not return together. So a closed loop of clocks can't be made self-consistent. Push them to different heights. And general relativity adds another mismatch. Time runs faster, higher up in a weaker gravitational field. So the clock on a mountain inexorably outruns the one at sea level. Add motion, and special relativity subtracts ticks for moving clocks, so satellites above you both speed up because gravity is weaker and slow down because they're moving. And the net is not a philosophical quibble, but tens of microseconds per day that real systems must correct. This is why global navigation works only after folding in relativity at every step. Receivers compensate for gravitational redshift, orbital speed, and Earth's rotation so that now at the satellite and now on your phone can be compared meaningfully. And even then, engineers carry extra corrections for signal paths that skim gravitational wells, Shapiro delays, and for the fact that the center of time used in Ephemerides is not Earth's surface, but the solar system's barycenter. If you scale up from hardware to geometry, the news gets stranger and clearer at once. The structure of space-time only gives everyone local nows, proper time along your own world line, and a partial order for events via light cones. For pairs of events separated so that no light or signal can connect them, relativity refuses to say which happened first because different observers sliding past each other slice space-time into different simultaneity layers. In flat regions, those slices are like different tilt angles through the same loaf. But in curved space-time, the real lumpy universe, there is not even a unique way to foliate the whole cosmos into global timesheets. So any talk of a universal present is a choice of coordinates, not a fact. You can get a sense of how hard the job is by looking at what the best clocks can already see. State-of-the-art optical clocks are so precise that lifting one by a few centimeters changes its rate measurably, turning metrology into a tool for mapping Earth's gravitational potential, relativistic geodesy, where now differs between the lab bench and the shelf above it. Particle physicists confront the same problem from another angle. When detectors thousands of kilometers apart look for a neutrino or a gravitational wave chirp, they cannot rely on a single civil time, so they discipline local oscillators to atomic ensembles and then translate all stamps into a carefully defined coordinate time, barycentric for solar system events, for example, before asking which detector rang first. In distributed computing, engineers gave up on universal now long ago and instead defined causality with happen-before relations, logical and vector clocks, or protocols that reach consensus rather than simultaneity, because networks, like spacetime, only guarantee that messages stay within their light cones. Even cosmology's seeming escape hatch, the cosmic time you get by averaging over galaxies at rest with the microwave background, doesn't rescue an absolute present. It's a convenient, large-scale clock tied to a particular frame. We know we're moving through it because we see a dipole warmth in the sky. But the laws themselves don't privilege that frame, and locally a fast spacecraft or a deep gravity well will still disagree with that cosmic schedule. Layer on the quirks of human timekeeping, and you see why everyday now is a pact, not a property. The SI second is pegged to an atomic transition so that physics, not planets, defines the tick. From that, we build TAI, a smooth count of seconds, UT1, Earth rotation time used by astronomers, and UTC, civil time that tries to stay near Earth's spin, and then glue them together with leap rules and broadcast them over fiber, radio, and satellites. It works brilliantly, yet every layer is an approximation, kindly ignoring that your now depends on altitude, motion, and path. If this all sounds abstract, notice its fingerprints in places that matter. High-frequency trading firms drag timing gear into co-location centers and still cannot define an absolute market now. So regulators and exchanges specify ordering by receipt within each venue. Power grids phase lock alternating current across continents without ever agreeing to a single timestamp beyond specified tolerances. Particle accelerators distribute sub-nanosecond timing over kilometers using fiber-based White Rabbit networks that continuously measure and cancel asymmetries. A technological confession that one-way time can only be trusted after two-way calibration. Even art museums that care about preserving digital pieces must choose whether a video installation's now is the file's embedded timecode, the display's refresh, or the audience's arrival. Different notions of simultaneity lead to different conservation practices. Press all of this into a single lesson, and it's surprisingly calming. The universe is not broken because it lacks a universal present. It is coherent because it replaces that dream with something sturdier. Local proper times, invariant causal, structure, and rules for translating between frames. The right question isn't, what is the true now? But, how do we compare intervals and order events so predictions stay consistent? And physics answers with a toolkit. Synchronize by exchanging signals and accounting for motion and gravity. Compute in coordinate times when you must. Fall back to causality when simultaneity dissolves. And design systems, technical and social, that don't collapse when the clock mismatch shows up. End softly here. Once you stop demanding a single cosmic clap, you gain something better, the ability to build truth from local ticks and light cone logic, and you learn to hear the universe, not as a metronome, but as a vast ensemble that stays in tune without ever playing the same beat everywhere at once. Causality breakdown, when effects exist without any cause. Start with a click that has no reason you can point to, a quiet lab, a sealed sample, and a Geiger counter that chirps anyway. No cosmic ray, no bump. Just a nucleus deciding to fall apart at a moment that no calculation, however careful, can predict. That's your first honest taste of causality breakdown. Not as magic or lawlessness, but as a limit on the kind of becauses the universe supplies. Because in quantum theory, the exact time a single atom decays has no deeper trigger. Its probability per unit time is set by the rules. Yet which instant wins is irreducibly random. Push on that discomfort, and you meet a second, sharper edge where classical causal stories truly fail. Split a pair of particles, and measure them far apart. And the correlations you see can violate Bell's inequalities. Patterns no local common, cause model can reproduce. So if you demand that each outcome be fixed by hidden instructions written at the source, you collide with experiments that close the obvious loopholes. Random and fast setting choices, space-like separation, even settings tied to light from distant quasars. The world refuses the tidy picture, in which every effect is screened off by a past cause. You could, in principle, measure. Yet notice what survives. No one uses these correlations to send messages faster than light. So, causality breakdown. Here is the death of one classical idea. Local preloaded causes, and the rise of a deeper rule. Non-local correlations constrained by no signaling. Shift to a stranger theater, where even the order of events can shrug. In certain quantum processes, there is no underlying fact of the matter about whether operation A happened before B or after it, and tasks performed in this causally non-separable regime can beat any strategy that assumes a fixed order, violating causal inequalities in the same spirit that Bell tests violate local realism. Again, nothing lets you text the past, but your old categories. First, then, stop covering the territory, and effect without cause becomes outcome without a single consistent ordering that explains it. Nature offers quieter examples that still bite. Spontaneous emission from an excited atom looks like light created from nowhere, yet in quantum electrodynamics, the vacuum itself has jitter, fluctuations that couple to the atom and set a decay rate. So the line you draw from causes to effect runs through a field with no classical counterpart. Hawking radiation at a black hole's edge and the Unruh effect for an accelerated observer extend the lesson. Particles appear because of horizons and accelerations that slice up field modes differently, not because someone lit a burner at a single place and time. So the cause lives in boundary conditions and geometry rather than in a local spark. The Wigner effect, pair creation in a strong electric field, drives the point home experimentally in materials like graphene, past a threshold. The vacuum of its electrons yields pairs that rip out of the field, yet no microscope shows a tiny match striking to start the fire. Down in condensed matter and quantum field theory, anomalies complicate the ledger. A current that classical equations say must be conserved can leak through quantum effects, with missing charge accounted for only by topological terms or flow from higher dimensional edges. Locally, it looks like an effect that snubbed a cause, until you expand your notion of where bookkeeping happens and see conservation restored globally. Even the second law, the most comforting cause-fey effect of daily life, phrase at small scales. Fluctuation theorems show that over short times tiny systems can run entropy backward, extracting work from noise with no daemon in sight. Violations that are lawful and expected when you watch single molecules or colloidal beads. So the cause of your macroscopic arrow is revealed as statistics, not commandment. The rule holds on average, but individual trajectories can and do make trouble, and there are optical tricks that seem to taunt causality without breaking it. In quantum tunneling, the group delay through a barrier can saturate so that thicker barriers don't add time. The Hartmann effect, tempting headlines about superluminal traversal. Yet careful analysis shows that the part of the wave that emerges was front-loaded in the incident packet, and that the front of any signal never outruns light. The effect before cause vibe is an artifact of how we summarize a reshaped pulse. If you work with data rather than atoms, the moral repeats in human terms. Simpson's paradox can flip a correlation sign when you aggregate groups. Bergson's paradox can conjure a spurious link when you condition on a common effect. And naive regressions can proclaim a cause is B, where a hidden confounder C pushed both. Effects that seem to bloom causelessly until you adopt the right causal graph and the right interventions. In quantum settings, even the graph language needs upgrades. Quantum causal models allow for non-commuting parents and show that some classical inference rules, like screening off by a common cause, can fail in the presence of entanglement, forcing you to replace, find the cause with, characterize the allowed interventions and the constraints they obey. The through line in all these cases is not chaos, but a change of ground rules, where classical intuition seeks a single, local, time-ordered shove for every shove back. Modern physics often gives you probabilities, global constraints, and pattern-level explanations, symmetries, conservation, boundary conditions. No. Signaling. That fix what can happen without naming a micro trigger for each event. At the level of a nucleus, the click has no deeper. Why now, at the level of two labs, a Bell pair has no local common cause. That explains its statistics. At the level of a process with indefinite order, there is no single timeline that fits all the facts. And in all of them, the wider framework, quantum theory, plus relativity, stays internally consistent and ferociously predictive. What do you do with this, besides wonder? You upgrade your questions, ask for constraints rather than culprits, for interventional recipes, rather than origin myths. In the lab you test no-go claims. By closing loopholes, and by building tasks that only a causal breakdown, in the classical sense, can beat. In engineering you design for irreducible randomness, with error bars, redundancy, and codes that don't care which electron flipped. In data you commit to causal diagrams, and to randomized or instrumented designs that can tell direction from coincidence. And in your own thinking you allow that some effects don't have causes smaller than the whole pattern they belong to. Because sometimes the truest, because the universe offers, is not a trigger, but a rule. End softly on that reframing. Effects without any cause turns out to be events without the kind of cause our ancestors expected. And learning to live with that calmly, precisely, and without superstition is the price of understanding a world that is stranger than a chain of pushes and better behaved than a chain of miracles. Quantum afterimages, shadows of events that were never real. Blink and notice the pale smear that lingers where a lamp used to be, an afterimage your eyes insist on, even though the light is gone, and carry that feeling into the quantum world, where some of the most trustworthy facts we can measure look like shadows of events that never quite existed as single, definite happenings. Begin gently with what shadow means here. Not a lie or a magic trick, but a pattern in correlations that no classical diary of who did what when could ever reproduce. Like footprints in sand that spell a sentence you couldn't have written by stepping left and right in any ordinary order. The cleanest entry point is the way physicists summarize joint possibilities that can't actually be jointly true, position and momentum together, or two incompatible measurements in a row, using objects called quasi-probabilities. These tables behave like probabilities most of the time, but can dip below zero in certain cells, a neon sign that says, no classical story fits. And those negative entries are not decoration. They can be reconstructed by tomography with light fields in a cavity, or by sequences of ultrasoft probes on atoms. And when you see them, you have learned something hard and real about your system, namely, that any attempt to assign it a single hidden history will fail. In a lab, the plot looks like this. Homodyne measurements of a small cat's state of light produce a Wigner map with alternating ridges and valleys, delicate interference fringes between two distinguishable lumps, and those fringes, neither bright nor dark in any one shot, only present statistically across many runs, are the afterimage of mutually exclusive classical stories that never took place yet, still affect. The outcomes you will later read shift from space to time, and the shadows sharpen. If the world always carried a definite value of a property that you could reveal without disturbing it, then time, separated measurements should obey the Leggett-Fagard inequalities. But dozens of experiments, from nuclear spins to superconducting circuits, have violated them, showing that the correlations across time cannot be explained by a creature that merely uncovered pre-written notes. What you actually see is subtler. The system's later answers carry the imprint of questions you might have asked earlier, and didn't. A paradox only if you insist on trajectories that never branch or blur. Engineers have learned to model this with quantum trajectories, records built from continuous, whisper, light monitoring. And when you combine the record you kept with the record you will later make, a method called smoothing, or the past quantum state, you can retrodict the most likely path the system took. That path is not film footage from a hidden camera. It is an afterimage carved in data that honors the rules while refusing to grant a single, definite sequence of intermediate facts. The same theme arises when you try to assign simultaneous truth values to a set of yes-no questions that cannot coexist. Contextuality theorems prove you can't, and their experimental tests draw shadows with numbers. Quasi-probabilities go negative or complex, telling you that any classical ledger of what was will contradict itself. Even our best pictures of flow in a two-slit experiment, average streams of momentum traced by extremely gentle probes, reveal smooth river lines that look like trajectories but are really statistical afterimages. The net push from many incompatible microstories, beautiful and predictive, yet never the path of a single particle you could have followed without changing it. If this still sounds like wordplay, notice the concrete ways shadows drive technology. In quantum error mitigation, we purposefully represent the effect of noisy gates as a combination of ideal ones with some negative weights, and then sample from that signed recipe. Nothing physically negative happens. You simply use the afterimage calculus to cancel bias in averages, a trick now standard in early quantum processors. In metrology, anomalous pointer shifts from carefully arranged probes can amplify tiny signals without actually asserting that a particle had an impossible value between measurements. The amplification lives in a shadow, the structured way many barely invasive touches add up. So you get a real sensitivity bias, while staying within honest limits. Modern non-equilibrium experiments go further, reconstructing full work distributions of small quantum engines and finding entries that no ordinary probability would allow. Afterimages again, that quantify how interference reshapes what can and cannot be said about what happened during a drive. And, in ultra-cold matter, researchers can measure out of time order correlations, deliberate scrambling tests whose very definition requires you to read shadows of non-commuting events, so that the growth of chaos itself becomes a traceable afterimage rather than a guess from blurred motion. Crucially, afterimage is not permission to hold contradictory beliefs. It is a warning label when incompatible questions meet. The world records a compromise in correlations, not a diary of mutually exclusive facts, virtual events. That equations so, mummen inside a calculation. Off-shell blips, intermediate states in a diagram, belong to this category too. They never occur as standalone happenings, and experiments confirm the shift rather than the ghosts. Even at the boundary of quantum and classical, the environment learns and republishes certain facts, so redundantly that they look immortal. The position of a dust speck bathed in light, the phase of a macroscopic superconducting loop, while fragile superpositions leave only faint interference marks, afterimages that vanish if you blink too hard, which is why everyday experience tempts you to believe in a single underlying script. The honest posture is to treat the shadows as first-class evidence, and the script as a useful approximation. End softly with the practical wisdom this yields. When a pattern in your data looks like a memory of something that never really happened, don't chase a single hidden cause. Write down the constraints, map the quasi-probabilities, and ask which questions you're allowed to combine. You will find that the most reliable knowledge in a quantum world comes not from pinning down a ghost, but from learning to read the afterimage. It paints across many careful glimpses. And once you do, the room grows quieter, your inferences grow sharper, and the strangeness becomes a tool rather than a scarecrow. The last tick: could physics predict the exact end of time? Pretend, just for a breath, that the cosmos sent you a calendar invite. Final tick: please RSVP, and feel how quickly the scientist in you pushes back. Whose tick, measured by which clock, and what exactly counts as time ending? Begin gently by laying out the terrain you can trust. Because physics is generous, here, there is no single universal metronome, only many proper times carried by world lines. So any last tick must be tied to a particular path, or a particular definition of what it means for change to stop. With that humility in place, you can tour the genuine ways a future might close, and ask whether any of them comes with a precise date. Some do not admit a date at all, only an asymptote. If expansion keeps coasting under a steady, positive push, and matter thins toward uniformity, the universe drifts toward a long quiet. Stars exhaust their fuel, black holes evaporate into a whisper of radiation. Gradients flatten, and novelty becomes rare. There is no calendar page labeled "the end." Just a slow approach to a state where almost nothing macroscopic happens, which means physics cannot stamp a day, because the concept of last dissolves into an ever-thinning tail. Other endings are sharper in principle. If the agent of cosmic acceleration is more impatient than a simple constant, if its pressure is so negative that it rips apart bound structures, then the scale factor would diverge in a finite proper time, and even molecules would be pulled loose. Here, a date could be computed if you knew that agent's behavior perfectly, but you don't. The parameter that sets the severity and its possible drift over time must be measured, and current observations allow a gentle range, not a verdict, so any countdown is really a forecast with error bars that could shrink or vanish. With better data, a different crisp ending belongs to a recollapsing cosmos, where gravity ultimately defeats the push and everything falls back together. Our best maps today favor continued expansion, but there is no theorem that forbids a turnabout if the driver of acceleration changes character. And again, the only honest answer is conditional. Give me the true law of that driver, and I'll integrate it forward. The starkest candidate for a dated doom is vacuum decay. If the field we call the vacuum is only metastable, then a tiny bubble of lower energy reality could appear somewhere by quantum tunneling and sweep outward nearly at light speed, rewriting the rules as it goes. That is not a screenplay but a worked-out possibility, and its crucial feature is statistical. You can compute a hazard rate from microphysics, yet the exact moment is intrinsically random. No precursor announces, now. No telescope can see the wall coming in time to warn you. So even a perfect theory would offer only odds per unit time, never an appointment. There are intimate endings too, real but local. Fall into certain gravitational wells, and your own proper time genuinely runs out at a terminal boundary, in a finite stretch, a personal last tick that no distant observer shares. Put these together, and you see why anyone who promises a universal date is selling certainties our best equations refuse to grant. Still, no date is not no science. Physics can draw a hazard map of endings, and sharpen it with observations, measuring the cosmic expansion across time via supernova surveys, the spacing of ancient sound waves fossilized in galaxy distributions, the fine pattern of primordial ripples still visible in the microwave sky, and even the tiny drift of redshifts over human decades constrains whether the push resembles a constant or something more volatile standard. Siren distances from gravitational wave events provide an independent ruler. Direct comparisons among the world's most precise optical clocks look for correlated wiggles that would betray a slow coupling between hidden fields and the units we use to measure time. Searches for proton decay or for exotic radiation test whether the deep book keeping that structure's matter has surprises waiting. On the theory side, the status of the vacuum in particle physics is read from the shape of a potential whose key numbers are tied to measured masses and couplings. Within uncertainties, today's best fit hints that our vacuum might be metastable, yet absurdly long-lived if no new particles intervene. Hardly a reason to sleep poorly, but strong motivation to measure better. Every one of these threads is a way of turning crude physics predict the end into how tightly can we bound the possibilities, and how quickly will those bounds improve. Even if a crisp scenario were favored, 3 stubborn limits would remain. First, prediction is never more precise than the concepts it hangs on. Heat death has no date, because there is a matter of definition, last star, last black hole, last bit flipped. And even a rip or a crunch gives different answers for different observers, because proper time is local. Second, the future can be chaotic in the technical sense. Tiny measurement errors today can balloon into big timing errors later, especially in nonlinear systems. So an exact tick can be replaced by a widening window, even when the overall story is fixed. Third, quantum irreducibility is not negotiable in processes. Like tunneling, hazard rates are calculable. Individual outcomes are not. Ask a nucleus, why now? And the only honest reply is the probability per unit time you already knew. Seen this way, the last tick is a mirror for what physics does at its best. It trades grand announcements for conditional clarity. It doesn't predict birthdays and funerals for the universe. It builds a catalogue of endings and tells you which evidence would move each one up or down the list. and it gives you a quiet, practical wisdom for the scale that matters to you. Because many plausible endings are asymptotic, or stochastic, or observer-dependent, the most meaningful last tick is not a date but a threshold. The moment a process runs out of gradients, out of records, or out of paths. And those are things you can watch. And even influence locally, end softly here, with the permission this grants. You don't need an apocalyptic timestamp to live scientifically. You need good priors, better measurements, and the discipline to distinguish hazard from hype. Build instruments that keep narrowing the space of futures. Keep asking which definitions of end you're actually using. And remember that the beauty of a universe without a scheduled finale is that it keeps rewarding careful attention right up to whatever counts as the last meaningful change.